It begins in silence. Not the kind of silence you experience when the world around you is asleep, but a silence that exists in the deep vacuum between the stars, a silence that has lasted for billions of years. Out here, in the interstellar darkness, sound cannot travel, and yet the absence of it feels deafening. This is the realm where the most dangerous object in the universe drifts unseen. It does not shine. It does not glow. It does not call attention to itself. It simply exists, patient, ancient, and absolute in its nature. Across the vastness, stars burn like scattered embers in an eternal night, each one a furious nuclear furnace screaming with light. Planets swirl around them, comets sweep their icy tails across the black, and entire solar systems spin like cosmic clockwork. But somewhere among this intricate machinery of gravity and light, there is a presence so extreme, so uncompromising in its physics, that it bends the very structure of reality around it. From the moment of its birth, it was unlike any other child of the cosmos, born not in gentle stellar nurseries, but in cataclysms, when the cores of massive stars collapsed under their own unimaginable weight, crushing matter into a singularity, a point of infinite density. Around it, a boundary formed, the event horizon, the ultimate point of no return. And yet, it is not deathly still. This thing consumes. Slowly, invisibly, relentlessly. It pulls not just on matter, but on the very fabric of space-time. If you could see it, it would appear not as an object, but as an absence, a perfectly black sphere where light itself vanishes. We call it a black hole. In the hierarchy of cosmic hazards, black holes occupy a place beyond comparison. Supernovae, gamma-ray bursts, rogue asteroids, all are destructive, but all are fleeting. A black hole is different. It is the embodiment of permanence. Once formed, it can persist for trillions upon trillions of years, outlasting the stars themselves. And they come in many forms. Some are the remnants of collapsed stars, a few kilometers across yet heavier than our sun. Others are supermassive titans, millions or even billions of solar masses, lurking at the hearts of galaxies. These are the architects of cosmic structure, shaping the growth of galaxies with their unimaginable pull. But the most dangerous kind is not necessarily the largest. It is the one you never see coming, a silent wanderer drifting through the void. Imagine for a moment a black hole no bigger than a city, carrying the mass of a star gliding invisibly through interstellar space. No light reflects from it, no heat radiates from its surface. The only evidence of its passage is the subtle warping of light from background stars and the strange, delicate tug it exerts on any object that dares pass too close. Such a thing could pass within the outer reaches of our solar system, and unless we were watching very closely, we might never notice until it was far too late. Humanity's understanding of black holes is still young. For most of history, even the idea of them was unthinkable. Newton's laws spoke of gravity as a force acting across empty space, but there was no hint of an object from which escape was impossible. In the 18th century, English geologist John Michel and French mathematician Pierre-Simon Laplace speculated about dark stars, so massive that light could not escape their gravity. But these were thought experiments, curiosities of mathematics, not real cosmic threats. It was only with Einstein's theory of general relativity in 1915 that the true nature of gravity came into focus. Space and time were not separate rigid frameworks, but a flexible fabric, bent by mass and energy. The greater the mass, the deeper the curve, and for certain masses within certain sizes, that curve became infinite, forming what Carl Schwarzschild soon calculated to be a singular solution to Einstein's equations. Even then, the concept felt too extreme, too absolute to be physically real. For decades, physicists argued about whether nature could truly allow such monsters to exist. But the universe, as it so often does, proved more imaginative than we were. Observations piled up, X-ray emissions from invisible companions devouring their stellar partners, the gravitational dance of stars around unseen masses, and finally, in 2019, the Event Horizon Telescope delivering the first image of a black hole's shadow. And yet, the more we learned, the more unsettling the picture became. The most dangerous object in the universe is not dangerous because it is violent in a cinematic, explosive way. It is dangerous because it changes the rules of reality around it. Time slows near it. Light bends into impossible curves. Matter is shredded at the subatomic level by tides of gravity. For anything that crosses the event horizon, the rest of the universe becomes unreachable forever. The black hole does not need to come to us in order to destroy us. If it merely wandered close enough, the delicate gravitational architecture of our solar system could be undone. Planets would drift from their orbits. Comets could be flung inward like cosmic shrapnel, and the Earth might find itself hurled into the icy darkness between the stars, or spiraling into a death plunge toward the event horizon. We do not know how many of these objects roam the galaxy. Estimates suggest there may be 100 million stellar mass black holes in the Milky Way alone, each one silent, invisible, and moving through space like a predator in the dark. Some are anchored to star systems, others drift alone, and in the immensity of time, their paths may one day intersect ours. Right now, as you read this, one could be approaching, a tiny shadow among the stars. There would be no warning flare, no blinding flash. Our only hope of detection lies in watching for the subtlest fingerprints, the dimming of a distant star as its light bends around an unseen mass, the faint tug on a spacecraft far from home, the mysterious acceleration of comets in the Kuiper Belt. For most of us, these signs would be invisible, noticed only by astronomers scanning the night sky with relentless patience. But if such a discovery was made, if the calculations confirmed that its trajectory would bring it within striking distance of our fragile world, what then? Even knowing would change everything. In the first days after such a discovery, the news would not reach the public. The data would pass quietly between observatories, encrypted emails exchanged between astrophysicists, and urgent meetings held in hushed tones. They would double-check the measurements, recalibrate the instruments, compare results from telescopes scattered across the globe. The numbers would be checked again and again, because what they would suggest would be almost unthinkable. A rogue black hole, perhaps only a few times the mass of the Sun, set on a slow but inevitable course toward the solar system. At first, its presence would be nothing more than a mathematical ghost, a faint gravitational lensing effect on the light of a background star, observed during a carefully timed survey. Over weeks and months, the pattern would repeat, the deflection growing slightly stronger as the object moved closer. Its path would be modeled with increasing precision, each iteration reducing the margin of error. The conclusion, in time, would be unavoidable. This black hole will pass through the outskirts of our planetary neighborhood. Even then, the danger would not be cinematic in its immediacy. Years, perhaps decades, might remain before the closest approach. But in cosmic terms, that is no time at all. And while the object would be too far to pull Earth directly into its grasp, its gravity could reach across billions of kilometers, disturbing the orbits of planets, destabilizing the fragile balance that has kept our world in a gentle spiral around the Sun for 4.5 billion years. In the mind's eye, imagine the black hole now, still invisible, still silent, but no longer impossibly distant. It drifts with an almost arrogant grace, untouchable by any force we know, wrapped in a halo of warping light from the stars behind it. As it moves, it leaves no trail, no wake, only a shifting distortion, as if reality itself ripples in its presence. The public revelation would come eventually, and it would arrive like a thunderclap. Headlines would scream about the cosmic threat, the wandering destroyer, the invisible killer. Social media would ignite with speculation, conspiracy theories, and apocalyptic predictions. Some would scoff, insisting it was overblown. Others would panic, imagining the Earth already doomed. The truth, as always, would be far more complex and far more unsettling. For while the black hole's direct impact might be avoided, the true danger would be the cascade of gravitational consequences it would unleash. Even a near pass could alter the orbits of the outer planets. Neptune might drift slightly inward, Uranus outward, the Kuiper belt thrown into chaos. Icy bodies the size of mountains could be hurled toward the inner solar system, their long looping journeys ending in collisions with planets, including ours. Over thousands of years, these changes would reshape the architecture of our cosmic home. To understand this, one must think not of the solar system as a set of isolated planets, but as a delicately tuned gravitational symphony. Every body, from the largest gas giant to the smallest asteroid, plays its part. The arrival of a rogue black hole is like introducing a new, deep, resonant note that reverberates through the entire composition, throwing the harmony into disarray. And yet, black holes themselves are not malicious. They are not predators in any conscious sense. They are simply the most extreme expression of gravity, nature's inevitability condensed into a singularity. In the heart of such an object, physics as we know it breaks down. The singularity is not merely a place of great density, it is a place where our current understanding stops working entirely. Time and space themselves end there, replaced by a mystery that no equation can yet fully describe. Approaching one is like approaching the edge of a waterfall you cannot see, hear, or feel until it is too late. For the unlucky matter that falls toward it, the journey is violent. At great distances, the pull is gentle, almost undetectable. But as you draw closer, the gradient of gravity becomes extreme. One side of you feels a stronger pull than the other, and the difference stretches you, a process known with grim poetry as spaghettification. Molecule by molecule, you are pulled apart, your structure unraveling in a final, irreversible descent. But from the perspective of a distant observer, something even stranger happens. As you approach the horizon, time itself appears to slow. You would seem to freeze at the edge, your image red-shifting, fading into darkness. In truth, you have crossed into a realm from which no signal can ever return. For you, the fall to the singularity continues. But for the rest of the universe, you have become an eternal shadow. This is the nature of the object now drifting toward us. It is both a physical presence and a philosophical abyss, a reminder that there are places in the universe where not just matter, but information, causality, and meaning itself vanish. Long before it reached the inner planets, the black hole's influence would be measurable. Spacecraft on the edges of the solar system, silent sentinels like Voyager 1 and 2, New Horizons, and future probes yet to be launched would detect anomalies in their trajectories. Their radio signals, timed with atomic precision, would reveal minute deviations caused by the extra gravitational pull. In response, the world's observatories would turn their gaze outward. Optical telescopes, radio arrays, infrared sensors, all would strain to catch any hint of the intruder. But the black hole would remain invisible except for the way it bends and magnifies the light of distant stars. These distortions would become more pronounced with time, like ripples in a lens moving across the sky. Plans would be drawn up, some practical, others fantastical. Could we launch probes to intercept it, to study the most extreme object in the universe up close? Could we use its gravity to slingshot future missions to unimaginable speeds? Could we, in some desperate way, influence its path? The cold reality is that the mass of a black hole is beyond manipulation. We could no more push it away than we could shove a mountain into another orbit. In the corridors of power, these discussions would take on a sharper tone. How much should the public be told? How should resources be allocated to monitor the threat? How do you prepare a civilization for something that cannot be stopped, only endured? The black hole, indifferent to all of this, would continue on its path, unhurried, unstoppable, ancient. It would have passed through other star systems before, scattering planets, igniting collisions, perhaps even swallowing entire worlds whole. To it, the solar system is just another waypoint on an endless voyage through the galaxy. And in the quiet spaces between the alarm and the waiting, a strange thought would occur. Perhaps we are not the first to watch such an approach with fear. Perhaps somewhere in the galaxy, countless civilizations have looked up at their skies, tracked a dark and silent wanderer, and wondered how much longer their world would remain in the light. Night after night, the skies would be combed for signs of the intruder. On mountaintops, in deserts, and in orbit above the clouds, telescopes would sweep the heavens with tireless precision. Astronomers would know that they could not see the black hole directly, so they would search for its fingerprint, the warping of starlight. When light from a distant star passes near a massive object, gravity bends its path. This phenomenon, predicted by Einstein and confirmed during a solar eclipse in 1919, is called gravitational lensing. The greater the mass, the greater the distortion, and in the case of a black hole, the effect is profound. A star that should appear as a single point of light might briefly shimmer, split, or brighten as the invisible lens passes in front of it. With careful observation and timing, scientists can calculate not just the mass of the unseen object, but also its velocity and direction. Weeks would pass, patterns would emerge. The black hole's trajectory would no longer be a vague possibility, but a calculated inevitability. Its approach would be slow enough to lull the careless into thinking nothing urgent was happening, but fast enough to send shivers down the spine of anyone who understood the scale of celestial motion. Objects in space, once on such a path, do not simply wander off course. To make sense of what was coming, scientists would model the solar system's future with supercomputers. These machines would simulate billions of years in hours, calculating how each planet, moon, asteroid, and comet would respond to the intrusion. The results would be sobering. In some scenarios, the inner planets remained largely untouched, spared the worst by the sheer distances involved. In others, the gravitational disruption would send icy missiles from the Kuiper Belt hurtling toward the Sun, crossing Earth's orbit in vast, centuries-long waves of impact risk. The mathematics would be as beautiful as it was terrifying. Orbital dynamics is a delicate art, a cosmic choreography where the slightest change can ripple outward in unpredictable ways. A tiny nudge to a comet in the outer solar system could send it on a course that would, millions of years later, intersect directly with our planet. The black hole's influence could set in motion a chain of events that would unfold long after it had passed, a slow-motion catastrophe written into the geometry of space itself. Public awareness would shift from curiosity to dread. In classrooms, children would ask their teachers if the black hole would swallow the Earth. In newsrooms, anchors would repeat scientists' careful reassurances that direct collision was almost impossible. But the word "almost" would hang in the air like a shadow. In the midst of this, astronomers would debate the black hole's origins. Where had it come from? Was it the remnant of a massive star that once shone in some forgotten corner of the galaxy? Or perhaps it was once part of a binary system, torn loose when its companion went supernova, flung into the galactic wilderness. Rogue black holes are wanderers without a home, set adrift by violent events, bound only by the slow drift of gravity across the Milky Way. Some would speculate about primordial black holes, hypothetical relics from the earliest moments after the Big Bang. These would not be born from stars, but from the chaotic densities of the newborn universe itself. If such objects exist, they could be anywhere, of any mass, from the size of a mountain to the size of an atom, though the latter would evaporate quickly through Hawking radiation. A stellar mass primordial black hole wandering near our system would be an unimaginably ancient artifact, older than any star, older than the Milky Way itself. As the months turned to years, the data would grow clearer. The projected path might indicate a pass through the distant Oort cloud, that vast halo of icy bodies encircling our solar system. This region, largely unexplored, is the cradle of long-period comets, those wanderers that take hundreds of thousands of years to complete a single orbit. A disturbance there could flood the inner solar system with comets for millennia. The sheer scale of it is difficult to grasp. Imagine standing on the surface of Pluto and watching the black hole sweep silently across the background stars. From that distance, it would still be invisible to your eyes, but the subtle shift in the heavens would be undeniable, a slow, steady distortion, like heat haze in the cold of space. The icy surface beneath your feet would tremble almost imperceptibly as the tidal forces reached across billions of kilometers to touch it. In deep space, far from any planet, an interstellar probe might pass close enough to feel the pull. Its trajectory would curve ever so slightly, and its onboard sensors would record a faint but measurable acceleration. Radio signals sent back to Earth would arrive a fraction of a second earlier than expected, betraying the invisible mass altering the probe's fate. These are the clues that tell a story across light years. And always, the object itself would remain silent, featureless, untouchable. No roar of destruction, no flare of light. Only its gravity speaks for it, and gravity has no need for haste. It works patiently, shaping the destiny of worlds without lifting a finger. For humanity, this would be a moment of deep reflection. Our civilization has faced threats before: asteroids, climate change, the raw power of our own weapons, but these are all problems we can at least attempt to solve with ingenuity, cooperation, and technology. A rogue black hole is different. There is no shield to raise, no engine powerful enough to alter its course. It forces us to confront the humbling truth that we are not the masters of the cosmos, but its passengers. And yet, we would not look away. The very danger of it would sharpen our curiosity and drive our scientists to study every nuance of its approach. Instruments would measure its mass, spin, and the shape of its gravitational field. Theorists would pore over equations, seeking insight into what lies beyond its horizon. There would be debates about sending a probe on a one-way mission, sacrificing the spacecraft, and perhaps human lives to cross the entry horizon and send back whatever data was possible before being cut off forever. Such a mission would be the ultimate gamble. It might tell us nothing, the probe's signals stretched and redshifted into oblivion. Or it might give us our first glimpse of the reality inside one of nature's most extreme laboratories, the place where time and space themselves are pushed to their limits. But even as plans were drawn and simulations run, the black hole would continue its inexorable drift, untroubled by our attention. It is not coming for us. It does not know we exist, but its path will brush against our home, and that will be enough. In the depths of space, danger often comes not in the form of sudden impact, but as a slow rearrangement of the cosmic order. The passing of a black hole is not an explosion, but a rewriting, a subtle shift in the celestial script that could echo for eons after it has moved on.
If the revised trajectory brought the black hole closer, far closer than anyone had dared imagine, the entire tone of the scientific reports would shift. What had once been a long-term theoretical concern would become an urgent problem with a countdown. The margin between a safe pass through the Oort cloud and a deep incursion into the realm of the giant planets would shrink, and suddenly the difference between cosmic curiosity and existential hazard would be measured in millions of kilometers. The first to notice would be the orbital dynamics teams. Their updated simulations would show the gravitational lines of influence twisting in ways that no one could dismiss. Jupiter's vast sphere of control over its moons and asteroids would warp like molten glass under the heat of an invisible forge. Saturn's rings, that delicate frozen architecture of ice and dust, could be pulled into chaotic spirals, scattering debris like shrapnel across the void. In the outer solar system, spacecraft would begin reporting strange deviations from their projected paths, not over decades, but in months. The Doppler shifts in their transmissions would tell the tale. The invisible mass was accelerating them, tugging them in directions no planned maneuver had ever intended. Even the Sun's gravitational dominance would be tested. Its clean elliptical orbits would warp, introducing tiny instabilities that, over centuries, could become catastrophic. From Earth, none of this would be visible yet to the naked eye. But for those watching the numbers, astronomers, physicists, mission planners, the sky would already be different. They would know the moment was coming when the black hole's influence would move from the abstract to the undeniable. And then the optical effects would begin. In the deep, unblinking gaze of the most sensitive telescopes, background stars would start to ripple. Points of light that had remained unchanged for centuries would briefly flare or bend, their photons redirected by the immense curvature of space-time. Around the black hole, a faint, perfect ring of light, an Einstein ring, might form for a fleeting instant as it passed in front of a distant star. No other object in nature produces such a precise, symmetrical distortion, and once seen, it would remove all doubt. For the first time, the public might glimpse the intruder, not directly, but through the artistry of physics. Images would circulate, a ghostly lens in the starfield, a halo of light where nothing should be. The news would report on it as if it were a photograph of some mythical beast finally caught in the wild, even though what they were seeing was not the thing itself,
but the mark it left upon reality. As it approached the region of the giant planets, the most immediate changes would be in the orbits of their moons. Jupiter's Galilean moons, Io, Europa, Ganymede, and Callisto, would shift slightly in their dance, their orbital periods deviating by fractions of a second at first, then by whole seconds. Titan, Saturn's great moon, might find its orbit elongated, pulling it into colder, more distant reaches or flinging it inward toward its parent planet. And then there would be the comets. The Oort cloud and Kuiper belt would erupt in slow-motion chaos. Bodies that had been locked in stable orbits for billions of years would be jolted into new trajectories, their long hibernations ending in drawn-out descents toward the sun. Some would be captured by the gas giants, their icy surfaces shattered into brilliant arcs of debris. Others would begin the long fall toward the inner solar system, their frozen surfaces awakening under the sun's light, shedding long, luminous tails. From Earth, these comets would become spectacular signs in the sky, bright streaks visible even in daylight, heralds of the gravitational storm unfolding far beyond our reach. In ancient times, such visions would have been taken as omens. Now they would be recognized for what they were, the visible consequence of the black hole's passing hand. But if the black hole's closest approach was measured not in tens of billions of kilometers, but in just a few billion kilometers, if it came deep into the territory between the outer and inner planets, then the changes would no longer be gentle rearrangements. The gravitational tides would grow extreme. Planets themselves could be pulled into subtly different paths, their years lengthened or shortened by seconds, then minutes. Over geological timescales, these shifts would change climates, tilt axes, and even alter the day-night cycle. For Earth, the first direct sign might come in the form of tiny, almost imperceptible changes in the Moon's orbit. Laser ranging experiments, bouncing beams of light off reflectors left by Apollo astronauts, would detect minute shifts in the Moon's distance. These, combined with delicate variations in Earth's rotation, measured by atomic clocks, would reveal that our world's gravitational environment was no longer constant. Space stations in orbit would also feel the difference. The International Space Station, tiny in mass compared to the Earth, would track just slightly differently against the background stars. Navigational satellites, which depend on precise predictions of orbital motion, would require constant recalibration. Every signal, every calculation would bear the faint watermark of the black hole's pull. And yet for all this, the object itself would remain invisible. No glare, no shadow, no surface to observe. Its presence would be known only through the dance of everything else around it. This is what makes such an approach so unsettling. You can witness the effects, but never the cause. As the day of closest approach neared, the scientific community would find itself in an impossible position. There would be no stopping it, no means of deflecting something with the mass of several suns. All they could do was predict, watch, and prepare for whatever changes it might bring. Governments would convene emergency sessions, not to plan a defense, there could be none, but to coordinate monitoring, public information, and, if necessary, disaster response. For ordinary people, the sense of unreality would be overwhelming. They would hear about gravitational tides and orbital instability, see artists' impressions of warped star fields and shadowed rings of light, but in their daily lives, nothing would yet be different. The sky would look the same, the sun would rise and set as it always had. The true scale of the approaching event would remain almost impossible to feel. But somewhere, billions of kilometers away,
Space itself would already be curling around a point of infinite density, and our solar system's familiar harmony would be subtly and irrevocably bending toward a new arrangement. The black hole would not hurry. It would glide past us with the indifference of a predator that does not even recognize its prey. And when it had passed, the solar system would never be the same. Some changes would be immediate: altered orbits, disrupted rings, comets in motion. Others would unfold over millennia, their origins long forgotten by whatever future intelligence inherited our place. The most dangerous object in the universe does not need to strike to kill. It only needs to pass close enough to touch.
The moment of closest approach would arrive not with a bang, but with a strange and eerie stillness. For weeks leading up to it, the scientific community would count down the days, hours, and finally minutes, updating trajectory models in real time as fresh data poured in from every spacecraft and observatory. Deep space antennas would hum with constant transmissions, their dishes tracking the point in the void where the intruder moved, a point so dark that it defied the imagination. Out in the distant reaches, the first witnesses would be machines. Probes stationed beyond the orbit of Neptune, long forgotten in the public consciousness, would awaken to send urgent signals. Instruments aboard would detect violent gravitational tides, subtle on the scale of planets, but overwhelming for a lone craft. Tiny deviations in velocity, minute changes in trajectory, all recorded with perfect precision, would flow back toward Earth across the cold gulfs of space. Nearer to the Sun, on the icy plains of Pluto, an observer, human or robotic, would see the stars begin to waver, not twinkle as in Earth's atmosphere, but bend. Constellations would distort slightly, their familiar shapes warping and stretching as the black hole's gravity pulled at the very path of their light. And if a distant star lay in exactly the right position behind it, an unearthly halo, an Einstein ring, would blossom for a moment, perfect and symmetrical, a silent revelation of what lay hidden in the dark. Closer still, around the giant planets, the effects would be more violent. Jupiter's magnetosphere, already vast and turbulent, would warp and compress in unexpected ways. Moons like Europa and Io would find their orbits subtly altered, their surfaces groaning under new tidal stresses. Io's volcanoes might erupt more violently, spewing plumes of sulfur into space. Ganymede's icy crust could crack in fresh scars, its hidden ocean stirring with gravitational tides that had not touched it for billions of years. Saturn's rings, fragile and ancient, would no longer be the serene bands seen in textbooks. The delicate balance of ice particles, shepherded by tiny moons, would be disrupted. Waves would ripple outward like shock fronts, scattering chunks of ice into chaotic paths. Some ring material might spiral inward toward Saturn, brightening its atmosphere with fiery impacts, while other debris would escape into independent orbits around the Sun. In the Kuiper Belt, hundreds of icy bodies would be jolted into new courses. Some would be sent plunging toward the inner solar system, their journeys lasting centuries. Others would be thrown into the depths of interstellar space, exiled from the Sun forever. And then the subtle fingers of the black hole's gravity would reach toward the inner planets. For Earth, the immediate danger would not be a sudden shift, but a gentle, persistent tug, just enough to disturb the intricate mechanics of our orbit. Satellites in high Earth orbit would drift out of alignment. Navigation systems would require constant recalibration. Space debris would begin behaving unpredictably, some fragments falling sooner than expected, others climbing into higher paths where they could remain for decades longer. From the surface, the signs would be more delicate still. Astronomers tracking the moon's motion with laser reflectors would detect a change of mere millimeters per day in its orbit, but over time those millimeters would add up to kilometers. Tidal patterns in Earth's oceans would shift fractionally, confusing long-established records.
Precision experiments measuring Earth's rotation would find the length of the day altered by milliseconds. But the most haunting effect would be in the night sky. Amateur astronomers, scanning the heavens, would begin to notice that some stars seemed wrong. Not gone, not dimmed, but subtly misplaced, as though the cosmic map had been redrawn. The distortions caused by the black hole's gravitational lensing would not vanish instantly after closest approach. They would drift slowly, lingering like ripples after a stone is thrown into a pond. On board the International Space Station, astronauts would float by the viewing windows, watching the dance of Earth below, blue oceans, swirling clouds, the blackness beyond, and know that somewhere out there, in the direction their eyes could not penetrate, the most dangerous object in the universe was passing. Instruments aboard the station would record changes in orbital mechanics, and the astronauts, highly trained and disciplined, would carry on their work knowing that history was unfolding silently just beyond their sight. For deep space missions, the passage would be more than a spectacle. It would be a trial. Spacecraft on the far side of the solar system might experience gravitational assists they never intended, their courses bent by the intruder. Some might gain speed and escape the sun entirely, propelled into interstellar darkness. Others might be pulled just enough to alter their planned flybys of asteroids or comets, their decades-long missions rewritten in a matter of hours. And through it all, the black hole itself would remain utterly invisible. No surface, no shadow, no light. If it passed near a dense cloud of gas or dust, it might feed briefly, producing a faint accretion disk, a whisper of X-rays detectable only by the most sensitive instruments. But in the vacuum of the outer solar system, there would be nothing for it to consume. It would remain a perfect, lightless sphere of nothing, seen only in the way it distorted the universe around it. As its closest point passed, the collective breath of humanity would not be released. The danger would not end instantly. The gravitational chaos set in motion would continue to unfold through centuries, perhaps millennia. It would take years for astronomers to fully understand the extent of the orbital changes, decades for the first comets dislodged by its influence to arrive near the Sun, and far longer for the deepest consequences to reveal themselves. But the event itself, the passing of a rogue black hole within the reach of our Sun's gravitational domain, would be remembered as a singular moment in the history of our species. For the first time, we would have seen not just the concept, not just the mathematics, but the reality of the most dangerous object in the universe moving through our home. And then, slowly, it would recede. The distortions in the stars would smooth out. The orbits of spacecraft would settle into new but stable paths. The gravitational tides would ease. The black hole would slip back into the galactic night, continuing a journey that had begun billions of years before humanity's first spark of intelligence, and that would continue long after we were gone. We would be left with altered skies, disrupted orbits, and the profound knowledge that we had been touched by something beyond all human scale.
In the months following the black hole's departure, the solar system would feel strangely unsettled, as though the familiar clockwork had been nudged out of alignment. To the untrained eye, the sun would still rise and set, the moon would still wax and wane, and the constellations would still march across the night sky. But for astronomers, every measurement, every calculation would now reveal a new and altered reality. The first changes would be found in the orbits of the giant planets. Jupiter's year might be shortened by a fraction of a day, Saturn's lengthened by the same. Neptune's path could be stretched into a slightly more elongated ellipse, its slow circuit around the Sun no longer matching the pristine predictions of Newtonian mechanics. On paper, these deviations might seem tiny, but on the scale of planetary dynamics, they were profound. Over centuries, such changes could ripple inward, subtly affecting the gravitational balance that kept the inner planets stable. The Kuiper belt would be in chaos. Hundreds, perhaps thousands of icy bodies would now be on altered courses.
Some would have been drawn deeper into the sun's influence, their long, dark orbits transformed into cometary paths that would bring them blazing into the inner solar system for the first time in billions of years. Others would be flung outward into interstellar space, becoming eternal wanderers like the black hole itself, their frozen forms carrying the fingerprints of our sun into the galaxy. The Oort cloud, that distant spherical reservoir of comets, would take far longer to reveal the full extent of the disruption. Some of its inhabitants would be jolted inward on journeys lasting hundreds of thousands of years. The first wave of these long-period comets might not reach the inner planets for centuries, yet their fates were already sealed in the moment of the black hole's passing. The solar system had been rewritten in slow motion. Closer to home, the Moon's orbit might carry the most immediate and measurable change. Laser ranging experiments, using the retroreflectors left by Apollo astronauts, would record millimeter-scale differences at first, but within a decade, the accumulated drift would become clear. The Moon was either receding faster than before or slowing in its retreat, depending on the direction of the black hole's pull. This shift, subtle as it was, could influence Earth's tides, weather patterns, and even the long-term stability of the planet's axial tilt. That tilt, the angle at which Earth spins relative to its orbit, is the hidden heartbeat of our climate. Small changes over tens of thousands of years drive ice ages and warm periods. If the black hole's passing had disturbed the gravitational interactions that keep our tilt stable, the climatic consequences might unfold slowly but inexorably over geological time. Space agencies would launch urgent missions to monitor the aftermath. New probes would be sent to the giant planets, their instruments tuned to detect minute changes in gravitational fields and orbital motions. Others would patrol the asteroid belt and the inner solar system, scanning for comets and meteors with altered trajectories. The aim would be not only to understand what had happened, but to prepare for whatever was coming next. For the black hole's influence was not limited to orbital mechanics. Its passing had also stirred up the interplanetary debris field, countless fragments of rock and ice that normally drift in harmless, stable paths. Now, some of these would be on collision courses with Earth and other planets. Most would burn up harmlessly in atmospheres, but a few, large enough to cause catastrophic damage, might arrive with little warning. In the skies of the coming decades, humanity would see an unusual spectacle, an increase in the number and brightness of comets. Some would be faint smudges visible only through telescopes. Others would blaze across the heavens, their tails stretching for millions of kilometers. These would be hailed as wonders, celebrated in photographs and headlines. But for planetary defense teams, each one would be a reminder of the lingering danger left behind by the passing intruder. Among the scientific community, there would be an almost obsessive focus on tracing the black hole's path. Every perturbation, every gravitational echo in the solar system would be plotted backward to reconstruct its exact course. The models would reveal that it had entered our domain at a steep angle to the plane of the planets, slicing through the solar system like a blade through water. Its trajectory would have intersected with no worlds directly, but its gravity had brushed them all. The public would be fascinated by the idea that this object, invisible, unstoppable, indifferent, had passed through our neighborhood and was now gone. Documentaries, books, and endless online speculation would follow. Some would imagine it as a kind of cosmic predator, others as a messenger from the farthest reaches of the galaxy. A few would wonder whether it had passed through other inhabited systems before ours, and whether any civilizations had survived its visit. But for scientists, the fascination was matched by a kind of lingering unease. This black hole had been found only because of chance, a specific aligning of background stars and the persistent observation of skilled astronomers. How many others were out there, unseen, moving along courses that might one day bring us close? Estimates would be sobering.
If the Milky Way contained hundreds of millions of stellar mass black holes, then statistically, some must be wandering relatively near our position. Most would pass harmlessly at great distances, but in the vast timescales of the galaxy, close encounters were inevitable. The event we had just witnessed might be rare on human timescales, perhaps occurring once every tens of millions of years, but in cosmic history, it was almost routine. Meanwhile, in the far reaches beyond Neptune, the slow domino effect of the black hole's passage would continue. Small, icy worlds would drift into new orbits. Some might collide, creating fresh clouds of debris. Others might reveal themselves for the first time to our telescopes, their surfaces glittering with the ancient ices of the early solar system. And deep beneath the surface of Earth's oceans, in the silence where sunlight never reaches, tidal forces would shift just enough to alter patterns of deep-sea currents. Over centuries, these could influence global climate in ways no one alive today would live to see. The black hole's gift to us would not be immediate destruction, but a slow, persistent rewriting of the background conditions in which life evolved. It would be tempting to think of the danger as past, the threat gone with the departing object. But for those who understood orbital mechanics, the truth would be harder to ignore. The solar system we had known was gone. In its place was a new, subtly altered system whose long-term stability had yet to be proven. The most dangerous object in the universe had passed us by, and yet its shadow would remain for millions of years. In the centuries after the black hole's passage, the most profound changes would be those that unfolded so slowly they would be invisible to any one generation. At first, humanity, if it still endured in recognizable form, would speak of the encounter as a great story of survival. The event would become history, then legend. And yet, long after the memory had faded, its fingerprints would continue to shape the destiny of our world. Climate would be among the first domains where the legacy became evident. If the black hole's gravitational nudge had altered Earth's axial tilt by even a fraction of a degree, the balance of sunlight over the planet's surface would shift imperceptibly. Winters might grow harsher in one hemisphere, summers more intense in the other. Over centuries, these small changes would accumulate, shifting weather patterns and ocean currents. Some regions that had been fertile might slowly dry into deserts. Others might see forests creep into what had once been frozen tundra. Ice sheets, sensitive to even the slightest changes in global temperature, would advance or retreat in patterns no longer matching the ancient cycles driven by Earth's orbital rhythms. The slow heartbeat of ice ages, once predictable, could be disrupted, their timing irregular, their intensity unpredictable. This would challenge every living thing, from the smallest plankton in the oceans to the largest mammals on land. In the oceans, altered tides would subtly change the deep circulatory systems that move heat and nutrients around the globe. These invisible currents, driven partly by the gravitational relationship between Earth and its moon, would respond over decades to the new orbital parameters. Entire marine ecosystems might be reshaped. Some species could vanish quietly, their loss noticed only when the intricate web of life they supported began to unravel. For humanity, if we were still a spacefaring civilization, the consequences would also be felt beyond Earth. Navigating the solar system would be subtly different in this altered gravitational landscape. Flight paths that once took months might now take weeks or years, depending on the positions of planets in their shifted orbits. Space stations and colonies on Mars, the Moon, or the moons of Jupiter and Saturn would have to recalibrate every aspect of travel, supply, and communication. The night sky would have changed too. Over centuries, the shifted positions of some outer planets and asteroids would slowly alter the background of constellations. Not in ways obvious to a casual observer, but enough that careful star maps would diverge from those drawn before the event. The distorted orbits of long-period comets pulled into new paths would create unpredictable celestial displays. Generations could grow up seeing multiple bright comets in a lifetime, a gift of beauty born from a passing threat. Yet beauty would come with danger. Those same comets, once rare visitors, could increase the risk of catastrophic impacts on Earth. Civilizations would need to maintain a constant watch on the sky, investing heavily in early warning systems and planetary defense measures. The black hole's legacy would not be a single moment of destruction, but a heightened, persistent threat stretching across millennia. In this altered solar system, the stability that had allowed life to flourish for billions of years would be in question. Planetary scientists would track the slow drift of orbital resonances, the subtle gravitational dances between planets that keep them in stable patterns. If those resonances shifted too far, chaos could creep in over millions of years, destabilizing orbits and sending planets or moons on unpredictable journeys. Earth itself might one day be nudged into a slightly different path, enough to trigger profound climate shifts or even eject it entirely from the habitable zone. And still, deep in the collective memory, the black hole's visit would linger. Across centuries, historians, poets, and scientists would weave it into the story of humanity's relationship with the cosmos. Some cultures might revere it as a cosmic trial we had passed. Others might see it as a warning, proof that the universe is not a safe harbor, but a wilderness of forces beyond our control. Meanwhile, astronomers would search the galaxy with a new urgency. The fact that we had survived one encounter would not blind us to the reality that there could be others. Every unexplained gravitational anomaly, every mysterious flicker in a distant star would be examined for signs of another rogue black hole. Space-based telescopes, free from the distortion of Earth's atmosphere, would sweep the darkness with unparalleled precision, not just mapping the stars, but the invisible masses moving among them. In time, perhaps thousands of years later, our descendants might even attempt to follow the intruder, not to stop it, for nothing could, but to learn from it. Probes or even crewed missions could be sent to chase its path into interstellar space, to study the relic from which it came. In doing so, they would confront the same mystery that has haunted physicists since the concept of a black hole was first imagined. What truly happens beyond the event horizon? The passing centuries would also reveal another, more philosophical consequence. The black hole's visit would have been a reminder, more powerful than any equation or theory, that humanity lives at the mercy of cosmic forces. For all our technology, for all our ambitions, we remain fragile creatures on a small planet, our fate tied to the delicate gravitational web of our solar system. If, in the distant future, that web were to unravel further, if the slow drift of orbits set in motion by the black hole's passing were to push Earth toward instability, then the event might be remembered not as a near miss, but as the first step in our eventual exile from the sun's warm embrace. But that would be measured not in centuries, nor in millennia, but in millions of years. The human mind struggles to grasp such spans of time. Civilizations rise and fall in the blink of a cosmic eye. In the long game of the universe, the black hole's passing would be only one move, but for us, it would have been the move that reminded us we are playing at all. And so, the altered solar system would turn on year after year under slightly different rules than before. Comets would fall, tides would shift, climates would change. Life would adapt, as it always has, but never again in quite the same conditions. The visitor would be gone, lost in the galactic dark, and yet its invisible hand would still be upon us. For this is the true nature of the most dangerous object in the universe. It does not need to destroy you outright. It only needs to pass close enough to change the story you are living forever.
Millions of years after the black hole's passage, the solar system would be a different place, not shattered, but re-sculpted. The quiet equilibrium that had lasted since the chaotic days of planetary formation would be gone, replaced by a slow, deliberate drift toward a new order. In the vast timeline of celestial mechanics, this would be the true echo of the intruder, not a sudden catastrophe, but a patient rewriting of the cosmic script. In this distant future, the subtle changes in planetary orbits that began as barely measurable deviations would have grown into undeniable shifts. Jupiter and Saturn, their gravitational influence magnified by their altered paths, could find themselves in a new resonance, their orbits synchronizing in a ratio that had never existed before. Such resonances, when stable, can preserve order, but when unstable, they can unleash chaos. Small imbalances might amplify, slowly nudging the orbits of the inner planets in unpredictable ways. Mercury, the smallest and most fragile in its orbit, would be most at risk. Even before the black hole's visit, simulations had shown that tiny changes over hundreds of millions of years could send Mercury into a chaotic state, possibly colliding with Venus or even falling into the Sun. Now, with the additional gravitational perturbation in its history, that instability might arrive much sooner. Further out, Mars could experience a gradual shift that pulls it closer toward Earth's orbit. The two planets might never collide, but their altered gravitational relationship could destabilize the asteroid belt between them. The result would be a slow rain of impacts over geological time, a bombardment far gentler than the great cataclysms of the early solar system, but persistent enough to shape the surfaces of worlds and influence the evolution of life. The Kuiper Belt, once a quiet outer province, would still be feeling the consequences of the black hole's passage. Entire families of icy bodies might have been displaced into long, looping paths that bring them perilously close to Neptune or Uranus. In some cases, these encounters could fling them inward toward the Sun. In others, they could be ejected entirely, set adrift into interstellar space. For any civilization living in this distant era, mapping these wandering worlds would be as important as tracking the motions of planets themselves. Far beyond even the Kuiper Belt, the Oort cloud would continue its slow unraveling. Comets dislodged during the black hole's passage would still be making their way toward the Sun, not in a single wave, but in a steady trickle across millions of years. This slow influx would ensure that bright, icy visitors remained a common sight in the skies of the future. For life on Earth or any other inhabited world, this would be a mixed blessing, a source of wonder and a source of danger. The climate of Earth, if it still hosted life, would reflect the accumulated consequences of these changes. If the black hole's tug had altered the planet's axial tilt even slightly, the long-term cycles of glaciation and warming would now follow a different rhythm. Some ice ages might be deeper and longer, others shorter and less severe. Entire epochs of life could be shaped by these subtle shifts. Species would evolve in response to climates no human had ever known, and some ecosystems that had endured for tens of millions of years could disappear entirely. If intelligent life still existed, it would likely have adapted to this new reality with a deep understanding of orbital mechanics and planetary defense. Early warning systems would track every significant object in the solar system, predicting their paths centuries in advance. Spacecraft might intercept comets long before they approach the inner planets, nudging them harmlessly away. Colonies on other worlds or in vast orbital habitats could serve as insurance against planetary disasters. Yet, even the most advanced civilization could not reverse the fundamental rearrangement set in motion by the black hole. They might prolong stability, but they could not restore the exact orbits and resonances that existed before. The solar system had been given a new trajectory in its own long evolution. And in the deepest, most far-reaching scenarios, the consequences could grow more dramatic still. Imagine a chain reaction. A destabilized Mercury plunges into the Sun, its gravitational absence subtly shifting Venus's orbit. Venus, in turn, begins to drift toward Earth's path, altering our planet's climate drastically. The asteroid belt sends more and more debris inward, triggering extinction-level impacts every few million years. In such a future, the solar system might never again enjoy the long, calm stretches that had allowed complex life to flourish. But there is even a greater possibility, one that would unfold over tens or hundreds of millions of years. If the new resonances between Jupiter, Saturn, and the other giant planets push the inner worlds into greater instability, Earth itself could be ejected from the habitable zone. Even a small shift in its orbit could trigger runaway greenhouse heating or a deep freeze. Over eons, the planet could become uninhabitable, leaving behind only traces of the life that once covered its surface. From a cosmic perspective, this would not be unusual. Planetary systems evolve, orbits change, worlds are lost and gained. The only extraordinary thing would be that this chain of events could be traced back to a single visitor, a rogue black hole that wandered through the solar system long before the final consequences played out. By this far future, the black hole itself would be unimaginably distant, perhaps tens of thousands of light-years away. It might have passed through other systems, scattering their planets, ejecting their comets, rewriting their histories as it had rewritten ours. Perhaps somewhere, another civilization would be looking at its altered sky, trying to understand the invisible hand that had shaped their fate. Back in the solar system, if intelligence endured, the memory of the encounter might still live on in ancient archives, a warning to those who would think of space as static and safe. Entire fields of study might be devoted to rogue black holes, their detection, and the prediction of their paths. Even so, the universe is vast, and the number of such wanderers is great. The lesson learned would be simple and humbling. In the wilderness of the cosmos, no place is truly secure forever. For in the end, the most dangerous object in the universe is not dangerous because it strikes without warning, but because it alters the fabric of your existence in ways you cannot undo. And it does so without intent, without malice, as indifferent to your fate as it is to the dance of the stars themselves. And so, millions of years after its passing, the solar system would continue along its altered course, the changes now so ingrained that they would seem natural to any who knew no other version of it. The black hole would be gone, but its shadow would remain, a shadow not of darkness, but of change. Hundreds of millions of years after the black hole's silent passage, the solar system would be deep into a new chapter of its history. The subtle rearrangements it left behind would now be inseparable from the grand, inevitable forces that shape all planetary systems over time. From the perspective of this far future, the black hole's visit would no longer be a recent scar. It would be woven into the very structure of the cosmos around us. By this point, the sun itself would have changed. Stars like ours grow steadily brighter over their lifetimes, and after billions of years on the main sequence, our sun's luminosity would be perhaps 10 to 20% higher than it was during the age of humans. This natural brightening alone would have been enough to slowly warm Earth's climate, but in a system already nudged off balance by the black hole, the consequences would be amplified. Even the smallest shifts in Earth's orbit, eccentricity, tilt, precession, would now have more dramatic effects on temperature and habitability. If the planet had not already been rendered uninhabitable by long-term climate shifts or orbital chaos, this brightening might tip it over the edge. Oceans could evaporate into the atmosphere, creating a runaway greenhouse effect much like that of Venus. The biosphere, if it still existed, would be dominated by heat-tolerant organisms, many of them descended from extremophiles that once hid in the hottest corners of the ancient Earth. The inner planets would fare differently. Mercury, if it had survived the gravitational reshuffling of earlier ages, would likely have been consumed by the Sun or ejected into a wild orbit long before this time. Mars might now be in a less predictable path, its surface an inferno regardless of distance. Mars, depending on its altered trajectory, might have passed through intervals of warmth and wetness, only to freeze again as its thin atmosphere failed to hold the heat. Further out, the gas giants would continue their slow migration. Jupiter and Saturn's resonances, perhaps modified permanently by the black hole's influence, could have pushed Uranus and Neptune into new positions. This migration, though far slower than the early grand tack movements that shaped the solar system, would still ripple through the Kuiper Belt and Oort cloud. New waves of comets could sweep inward, creating impact events on the remaining habitable worlds or moons. And yet, even with all this slow chaos, life might still persist, though perhaps not on Earth. The moons of the outer planets, like Europa, Enceladus, or Titan, could be refuges for biology, protected beneath thick ice or dense atmospheres. The black hole's ancient gravitational stirring might even have enriched these worlds, increasing tidal heating and maintaining liquid oceans for eons longer than expected. In some timelines, an intelligent civilization, perhaps descended from humanity, perhaps entirely alien, could thrive here, aware of its place in the altered solar system. For them, the story of the black hole would be an origin myth and a cautionary tale. They would understand their sky not as fixed, but as something dynamic, shaped by forces that can arrive without warning from the deep dark between the stars. Meanwhile, the black hole itself would be unimaginably far away. In the hundreds of millions of years since it had passed through our cosmic neighborhood, it would have traveled thousands of light years, slipping between the spiral arms of the Milky Way. It might have grazed other planetary systems, scattering their worlds as it had ours. In its passage, it would remain forever silent, without witnesses, unless another civilization detected it and traced its path back through the galaxy's records. Closer to home, the gradual brightening of the Sun and the shifting gravitational balances could conspire toward a final instability in the inner system. Perhaps Jupiter and Saturn's altered orbits would eventually send Mercury or Mars into a crossing trajectory with another planet. Such collisions, while rare, are possible in chaotic orbital systems, and the energy released would be catastrophic on a planetary scale. The debris could form new moons or rings, or be cast out into interstellar space as yet more cosmic wanderers. Even the asteroid belt might undergo a slow but profound transformation. Over the eons, gravitational nudges could herd its rocks into unstable orbits, triggering periodic asteroid storms in the inner system. Any surviving biosphere would need to adapt to these cycles of devastation. In some ways, this might act as an evolutionary driver, forcing life to change and diversify or perish. Eventually, on timescales of billions of years, the Sun's aging would become the dominant force in the system's fate. Long before it swelled into a red giant, its growing heat would strip Earth's oceans, sterilize its surface, and drive away its atmosphere. Any life that endured would need to be nomadic, moving outward to colder worlds or to artificial habitats orbiting far from the Sun. By then, the black hole's influence would just be one thread in a tapestry of cosmic events that had shaped the solar system, no more recent than the violent birth of the planets or the great bombardments of the early eons. Yet, for the inhabitants of this distant age, the black hole would remain a symbol of something far greater, the knowledge that the universe is not a static backdrop, but an ever-changing, unpredictable stage. In rare cases, gravitational interactions between the altered solar system and passing stars might even set the stage for another rogue black hole encounter. The galaxy is vast, but in billions of years, paths can cross again. If such an event occurred, it would meet a system already scarred by the memory of the first. Whether its inhabitants would be ready, or even exist at all, would depend on the resilience and adaptability of whatever intelligence remained. And so, in this far future, the solar system would drift onward, a place both familiar and alien compared to its ancient self. Planets would still turn, comets would still blaze, and moons would still circle their primaries, but all in patterns subtly rewritten by a visitor that came and went in silence, long before the sun began its final transformations. Somewhere, in the annals of whatever knowledge endured, there might be a record of it, the moment when the most dangerous object in the universe passed near, changing everything without ever touching a single planet. A moment when gravity itself reached across space and time to alter the fate of worlds. And perhaps if any consciousness still gazed into the dark between the stars, they would wonder how many more such wanderers were out there, and whether one might already be on its way.
A billion years after the black hole's passage, the solar system would be deep into the slow twilight of its middle age. The sun, no longer the same star that warmed the Earth in the days of humanity, would shine brighter and hotter, its nuclear heart consuming hydrogen at an ever faster pace. This increase in luminosity would have profound consequences for every surviving world, and the delicate gravitational changes left behind by the black hole would still be shaping how those worlds lived or died beneath its light. Earth, if it still existed, would be unrecognizable. Long before this point, the oceans would have boiled away, stripped into space by the sun's intensified radiation. The continents, bleached and cracked, would be baked beneath an atmosphere heavy with water vapor and carbon dioxide. The biosphere that once flourished here would be gone, replaced by a barren wasteland more hostile than present-day Venus. Any life would have retreated to hidden refuges, perhaps underground or in the high atmosphere, or it would have abandoned Earth entirely. If intelligence had endured, it would have moved outward long ago, to colder domains where the sun's increased heat could still be balanced into habitability. Mars might have been warmed enough to host oceans for a time, but its thin atmosphere would eventually give way, forcing migration further still. The moons of the outer planets, Europa, Ganymede, Titan, and Enceladus, would have gone through their own transformations. Tidal heating, altered by the gravitational shifts seeded by the black hole, might have prolonged their subsurface oceans for millions of years beyond expectation. Now, under the sun's hotter glare, some could have thin surface seas, gleaming under pale skies. In this age, the gravitational scars left by the black hole would still echo through the orbits of the planets. Even now, Jupiter and Saturn's relationship could be slightly different than in the ancient past, perhaps just enough to alter the flow of comets and asteroids inward. The inner system, already stripped of oceans and life, might still be bombarded by icy remnants from the Kuiper Belt and Oort cloud, their trajectories warped long ago. Impacts on a dead Earth would create brief, dazzling explosions of light, like cosmic fireworks over a world that could no longer watch them. Beyond the planets, the black hole's influence might still be visible in the population of free-floating objects wandering the system. Entire asteroids and dwarf planets, ejected into eccentric orbits by its ancient passing, could still be looping through space in long, slow arcs. Some might have even been stolen away entirely, cast into interstellar space, to drift between the stars forever, silent ambassadors of a system forever changed. Meanwhile, the sun's growing brightness would set the stage for its final act. As it approached the end of its hydrogen-burning phase, it would begin to expand. Over tens of millions of years, its outer layers would swell, turning it into a red giant. Mercury, if it had not been lost earlier, would be the first to fall, swallowed by the expanding stellar surface. Venus would follow. Whether Earth met the same fate would depend on the exact balance between solar expansion and mass loss. But even if spared engulfment, it would be scorched beyond recognition, its rocks glowing faintly in the relentless heat. The gravitational rearrangements caused by the black hole might influence these final stages in subtle ways. Altered planetary orbits could change the timing of resonances that govern the stability of the inner system. If, for instance, Earth's distance from the Sun had been slightly shifted by the event, it might either escape or hasten its consumption during the red giant phase. The fate of Mars, too, could hinge on these ancient perturbations, determining whether it would be engulfed or survive as a scorched, airless shell orbiting a bloated sun. Farther out, the giant planets and their moons might experience a strange renaissance. The increased sunlight could warm some icy worlds into fleeting habitability, melting surfaces frozen for billions of years. For a time, Europa's crust might crack open into vast, shallow seas. Titan's methane lakes could evaporate, replaced by water oceans beneath hazy skies. If any remnants of life had taken refuge in these worlds, they might emerge to explore a brief new era of warmth before the sun's further evolution turned their homes into deserts. But this renaissance would be short-lived. The red giant sun would eventually shed its outer layers into space, creating a vast, glowing planetary nebula. The inner planets, or their charred remains, would be stripped of whatever atmospheres they still had. The nebula's expanding gas would sweep outward, mingling with the altered debris field left by the black hole's passage so long ago. In this way, the legacies of two cosmic events, one a slow stellar death, the other a wandering gravitational disruption, would merge into a single transformation of the system. When the sun's core settled into a white dwarf, the solar system would enter its final, long epoch. The surviving planets, moons, and debris would orbit a faint, hot ember of a star, bathed not in the golden warmth of the past, but in a cold, bluish light. By then, the black hole's direct influence on their orbits would be ancient history, but the rearranged architecture it created would still define their paths. The cometary reservoirs, if any remained, would be sparser but not empty. Every so often, a survivor of the Oort cloud could still plunge inward, drawn by gravitational resonances set in motion billions of years earlier. Perhaps in this far age, the solar system would still host intelligence, not on the surviving planets, their surfaces would be cold and airless, but in vast space habitats orbiting the white dwarf, drawing on its residual energy and the resources of asteroids and moons. For such beings, the history of the black hole's passage would be as distant as the earliest days of the sun's birth, a piece of ancestral memory recorded in archives and simulations. And yet they would still feel its presence in a way. Their home system would be a subtly different place than it might have been without that encounter. Planets in slightly different places, belts of debris shaped differently, certain worlds missing that might otherwise have endured. They might trace their entire history, even their survival, back to that silent visitor. If the black hole had passed closer, perhaps the system would have been destroyed. If farther, perhaps it would have remained unchanged, leaving them to face the sun's death with a different arrangement of worlds. The irony would be that by this point, the black hole itself would be somewhere else in the galaxy entirely. perhaps thousands of light-years away, influencing another system in ways its victims could never guess. The same silent reshaping would go on century after century, star system after star system, the invisible signature of the most dangerous object in the universe. And in the cold, fading light of the white dwarf, the solar system would endure, altered, diminished, yet still orbiting, still turning, a relic of two great forces, the life cycle of a star and the chance passing of a cosmic wanderer whose touch had changed it forever.
Tens of billions of years after the black hole's passage, the solar system, if it could still be called that, would be a ghost of its former self. The sun, long since shed of its outer layers, would have cooled into a dark, cold white dwarf. Its faint glow would no longer warm any orbiting body. Instead, it would drift through the galaxy like a cosmic ember. Around it, only a few survivors would remain: distant planets, icy moons, and scattered debris, all moving along altered paths written into the system's fate by the black hole's ancient influence. In this age, the galaxy itself would be a different place. Star formation would have slowed almost to a halt. The spiral arms would have lost much of their luster, their great nebulae gone dark as the raw material for new suns was exhausted. The remaining stars would be older, redder, dimmer, a quiet galactic graveyard where only the most long-lived stars still burned. Black holes, however, would be plentiful. Many would be the remnants of long-dead stars, but others, like the one that had once brushed past our home, would still wander the dark between systems, unaging and unchanging. In the deep future, these objects would become the dominant architects of the galaxy's structure. Their gravity would continue to reshape planetary systems, pull on stellar remnants, and perhaps on rare occasions merge with one another in cataclysmic events that sent ripples through the very fabric of space-time. The white dwarf that had once been our sun would still hold on to some of its planets, though their arrangement might bear little resemblance to the original solar system. Over billions of years, gravitational interactions, amplified long ago by the black hole's passage, would have rearranged orbits, ejected some worlds entirely, and thrown others into slow, decaying spirals toward their cold, dim star. The survivors would be locked in a frozen stillness, their surfaces covered in eternal ice, their atmospheres, if any, condensed onto the ground. If any artificial structures still existed, ancient space habitats, asteroid mines, or colonies built by descendants of humanity, they might now orbit far from the white dwarf, drawing energy from other sources. The slow decay of radioactive materials, the faint heat of the stellar remnant, or even the manipulation of gravitational energy itself. Such civilizations, if they endured, would measure time not in centuries or millennia, but in spans that rival the ages of stars. The memory of the black hole's passage would by now be unimaginably ancient. If any records survived, they might be preserved not in paper, stone, or even digital form, but in patterns etched into the very matter of constructed worlds. Perhaps a vast archive would orbit the white dwarf, its data encoded in crystals designed to last longer than planets. Inside, the account would be clear. Long ago, a black hole entered the solar system, altered its structure, and moved on. The story would stand as both history and warning, a reminder that even in the quietest eras of the cosmos, danger drifts unseen. Beyond the shrunken boundaries of the system, the galaxy's gravitational tides would continue to pull. Over immense timescales, even the sun's remaining planets might be stolen by passing objects, other stars, rogue planets, or yet another black hole. In the deep time ahead, the idea of a stable system would vanish entirely. The galaxy would become a place of slow collisions and exchanges, where no orbit was truly permanent. Eventually, perhaps after hundreds of billions of years, the white dwarf itself would cool into a black dwarf, a body so cold and dark that it would radiate almost no heat at all. Around it, the surviving planets would be invisible, detectable only by the faint gravitational influence they exerted on one another. In that frozen dark, the only warmth would come from tidal heating in moons still locked in uneven orbits, or from the rare, spectacular arrival of a comet or asteroid, whose fall released a final burst of energy into an otherwise silent system. The black hole that had passed so long ago would still exist, unchanged, somewhere in the galaxy. Perhaps it would now be part of a binary system with another black hole, spiraling together until they merged in a brief but violent blaze of gravitational waves. Or perhaps it would still roam alone, having crossed thousands of light years, its influence scattered among countless systems that had never seen it coming. In this late age of the universe, its kind would be among the last active participants in cosmic evolution. For in the far, far future, when stars are gone and only stellar remnants remain, black holes will still shape the universe. They will consume what is left: gas clouds, asteroids, planets, and even the faint light of the cosmic microwave background, slowly growing as the rest of the cosmos fades. The black hole that once touched our system could, in unimaginable time, be one of the last great masses left in the galaxy, a dark monument to the forces that govern existence. By then, the descendants of humanity, if they survived the death of their star, might live far from here, in systems untouched by that ancient visitor. Perhaps they would have migrated into artificial habitats orbiting supermassive black holes, using their energy as the last reliable power source in a dying universe. Perhaps they would remember their origins in a blue world that no longer exists, orbiting a star that has long since gone cold. In the infinite quiet of this age, there would be no dramatic reminders of the black hole's visit, no warped rings of light in the sky, no comets blazing inward from the dark. Its legacy would be in the orbits of long-dead planets, in the trajectories of asteroids, and in the very arrangement of whatever remained bound to the cold husk of the sun. The most dangerous object in the universe had come and gone without a sound, and yet, billions of years later, its influence would still be written into the motions of the last survivors. And in the vast emptiness between the stars, the black hole would glide on, indifferent as ever, carrying with it the power to change the fates of worlds without ever touching them. It would outlast the stars, the planets, and perhaps even the galaxies themselves. In the end, when the universe reached its farthest, coldest, most silent moment, it might still be there, one of the final actors on the stage, waiting in the dark for a new chapter that may never come. Tens of trillions of years after the black hole's ancient visit, the universe would be deep in what cosmologists call the black hole era. Stars would be gone. Their light, which once traced the graceful spirals of galaxies, would have faded into darkness billions of years earlier. The Milky Way itself, or what remained after countless gravitational mergers, would no longer be the familiar disk of shimmering stars, but a diffuse collection of stellar remnants, and above all, black holes. The solar system, if it still existed in any form, would bear no resemblance to its early self. The sun, long cooled into a black dwarf, would be completely dark, indistinguishable from the frozen planets, if any remained bound to it. In this age, the only visible light would come from rare and violent events, collisions between black holes, or the evaporation of the smallest ones through Hawking radiation. These flashes would be brief and precious, tiny sparks in a sea of eternal night. The black hole that once passed through our neighborhood would still be here, unchanged and eternal on human timescales. It would have roamed the galaxy, or what was left of it, for untold eons, its gravity shaping the paths of any objects that drifted too close. Over trillions of years, it might have merged with others, growing in mass and altering the invisible architecture of space. Each merger would have sent ripples through space-time, gravitational waves spreading outward at the speed of light, though there would be no one left to witness them. In this era, black holes would be the rulers of the cosmos. Stellar mass black holes, like our ancient visitor, would share the darkness with supermassive ones, each millions or billions of times the mass of the Sun. These giants, anchored at the centers of what used to be galaxies, would slowly consume whatever matter still wandered near: rogue planets, brown dwarfs, white dwarfs, neutron stars, even other black holes. Over unimaginably long spans of time, Hawking radiation would begin to erode them. Though this process is glacially slow for massive black holes, far longer than the current age of the universe, in the black hole era, time is plentiful. One by one, the smallest would fade, their mass transformed into a faint, final drizzle of particles, disappearing with a soft whisper into the void. Our visitor, if it remained relatively small, might be among the first to vanish in this way. But before that end, it could continue its silent influence, passing through the orbits of dead worlds, scattering them like dry leaves in a wind. Some of these worlds could be survivors from our solar system, frozen and inert since the death of the Sun. Others might be interstellar refugees from systems long gone, captured during the galaxy's slow collapse into gravitational clumps. It is even possible that remnants of civilizations, if any endured this far, could choose to live near black holes in this era, not because of any threat, but because a black hole could be the last reliable source of usable energy in the universe. Matter falling into its event horizon would release incredible amounts of energy as heat and light in the surrounding accretion disk. Even the faint glow of Hawking radiation from a small black hole could be harnessed by unimaginably advanced technologies to sustain life in a universe that had otherwise gone dark. If such beings existed, they might know the story of this particular black hole, tracing its path back through trillions of years to a moment when it had passed near a small, blue, living planet in the distant past. For them, this would be less history and more mythology. A tale from the dawn of time, from the universe's brief, bright youth. They might build monuments to it, orbiting just outside the event horizon, riding the edge between safety and the ultimate plunge. But eventually, even this age of black holes would end. Over timescales so vast that they defy comprehension, far beyond trillions, into numbers with dozens of zeros, Hawking radiation would drain even the largest black holes. Our ancient visitor would shrink, imperceptibly at first, then faster as its mass decreased. In its final moments, it would release a burst of radiation, its mass converted entirely into energy, a last flash of existence before vanishing forever. By then, the universe would be almost empty. The matter from which galaxies, stars, and planets were built would be gone, spread so thin that it would be indistinguishable from the vacuum. Only a sparse mist of subatomic particles would remain, drifting in an ever-expanding void. The last black holes, supermassive titans that once ruled entire galaxies, would wink out one by one, leaving nothing behind but the cold geometry of space-time. In that final, silent cosmos, there would be no worlds to remember the black hole's journey, no eyes to witness the end. And yet, in a sense, its influence would still remain, encoded in the structure of the universe itself. The galaxies it had passed through, the systems it had altered, the paths it had deflected, all of these would have been part of the grand, interconnected web of cause and effect that shaped the fate of everything. Our solar system, if any trace of it still lingered, would now be nothing more than a few scattered particles, too far apart to interact meaningfully. The memory of its sunrises and oceans, its civilizations and histories, would be gone.
absorbed into the anonymous dust of the cosmos. The only record would be in the deep past, a past that could never be revisited, for time in this universe flows only forward. And so the black hole's story, and the story of its brief encounter with a small, fragile world, would end not with destruction, but with dissolution, not with an explosion, but with a quiet fading into the dark. For all its danger, for all its ability to reshape the destiny of planets and stars, it too would be a mortal thing in the face of eternity. The most dangerous object in the universe would share the same fate as everything else, to vanish, leaving only the silence and the infinite expansion of space behind. The black hole left the solar system in silence, just as it had arrived. No flare of light marked its departure, no shockwave rippled outward. It simply continued along its path, gliding through the fabric of space-time with the same indifference that had carried it across the galaxy for billions of years. Behind it, the solar system was subtly changed, a rearranged collection of worlds, moons, comets, and dust, whose orbits now carried the faint but permanent signature of the visitor's passage. Ahead of it stretched the unbroken dark between the stars, a wilderness without landmarks or borders. For the black hole, there was no destination, no memory, no purpose, only the inevitability of motion under the weight of its own gravity. It moved at several hundred kilometers per second relative to the sun, an unstoppable drift born from ancient violence. Long ago, perhaps in the chaos following a supernova, it had been flung from its birthplace with tremendous speed. Since then, it had crossed spiral arms and inter-arm voids, skirted the edges of stellar nurseries, and passed unseen by countless stars. Now, as it journeyed outward from our system, the first to feel its influence would be the most distant members of the Oort cloud, icy bodies so far from the sun that they lay halfway to the next star. These frozen relics of planetary formation, untouched for billions of years, would shift in their orbits, their delicate balance disturbed. Some would be pulled slightly inward, beginning the long fall toward the sun. Others would be ejected entirely, joining the countless rogue objects that wander the galaxy. The black hole's trajectory carried it on a gentle arc through the galactic plane. Ahead lay vast clouds of interstellar gas and dust, the remains of long-dead stars and the raw material for new ones. But the black hole would not ignite them, for it had no luminous breath. Only if it passed directly through a dense enough region might it feed, pulling matter into an accretion disk and releasing a faint, deadly glow of X-rays. Most of the time, it would pass through the galaxy invisible, detectable only through its warping of light from faraway stars. It crossed the dark outskirts of our spiral arm, moving toward a region sparsely populated with stars. These inter-arm gulfs were quieter than the crowded lanes of the Milky Way's spirals, but they were not empty. Here drifted solitary red dwarfs, old white dwarfs cooling into black dwarfs, and the occasional neutron star, each a relic of a stellar life now long over. The black hole passed them like a shadow, their paths bending slightly in its presence, their light bending more. Over tens of thousands of years, it closed the distance to its next near encounter, not with a living burning star, but with another wanderer, a rogue planet. This world had once orbited a sun-like star before being flung free during the violent reshaping of its system. Now it drifted through the dark, its surface frozen under a crust of nitrogen ice, its atmosphere long since collapsed to the ground. The black hole and the planet passed within a few million kilometers of one another, their mutual pull altering each other's courses ever so slightly before they continued on their separate ways. Farther ahead, in another 100,000 years, lay a more dramatic meeting, a close pass by a red dwarf star. The black hole's approach would not threaten the star's life, but it would stretch and twist the paths of its orbiting planets.
The innermost world, already scorched by proximity to its dim, cool sun, might be pulled just enough to destabilize its path. Over centuries, it could spiral inward, vanishing beneath the red dwarf's surface. An outer, icy planet might be drawn outward into a more distant orbit, its frozen surface locked in a colder night. For any civilization that might have existed in that system, if it had survived the tight gravitational leash of a red dwarf, the black hole's arrival would be a rare and incomprehensible event. They would watch as the sky shifted unnaturally, as background stars warped and split into ghostly arcs of light. And then, without a sound, the intruder would pass, leaving their world forever changed. The black hole's journey was not a straight line. The galaxy's gravity, uneven and restless, curved its path in a great slow dance around the galactic center. Over millions of years, it would trace an elongated orbit, carrying it through different regions of the Milky Way, from crowded stellar neighborhoods near the spiral arms to the empty, dark gulfs beyond them. Some of these passes would bring it near the edges of star-forming regions, vast clouds lit by the ultraviolet glow of newborn stars. Here, its gravity might quietly alter the fate of future solar systems, tugging on the drifting clumps of gas that would one day collapse into suns and planets. In this way, without ever touching them, the black hole could change the destiny of worlds that would not even exist for another 100 million years. Every so often, it would pass near another black hole. These encounters were rare and distant, but their gravitational embrace could fling both objects into new trajectories, or in the rarest of circumstances, draw them into a spiraling merger. Such an event would release a final deafening shout into space-time, gravitational waves powerful enough to ripple across the galaxy. But most of the time, the black hole's existence was one of absolute solitude. No light, no heat, no surface, just an endless journey through a universe that had no map and no destination. If it had memory, it might recall the brief moment it passed through the solar system, the worlds it shifted, the comets it set loose, and the fragile blue planet that spun so close to its star. But it had no such capacity. It was a thing of pure gravity, unknowing and uncaring, bound only by the laws of physics. Yet in that absence of awareness lay a strange poetry. The black hole's life was not measured in moments or choices, but in the quiet, invisible reshaping of the galaxy itself. Over the aeons, it would influence countless orbits, trigger the birth of new worlds, and end the stability of others. The legacy of its path would be scattered across the Milky Way, a tapestry of altered systems, each bearing the faint imprint of a passage that lasted only an instant on the scale of eternity. And somewhere far behind it now, the solar system turned on in its new, altered form, carrying forward the gravitational mark it had been given. Perhaps millions of years from now, some new intelligence there would point their instruments outward, detect the faint lensing of starlight, and realize that the ancient visitor had been found again, still moving, still silent, still the most dangerous object in the universe. After leaving the relatively quiet inter-arm region, the black hole's long orbit around the Milky Way's center gradually drew it toward a denser stretch of the spiral arm. Here, the darkness was punctuated not just by isolated stars, but by clusters, glowing nebulae, and clouds so vast they could give birth to thousands of suns. The first sign of entering such a region was the increased frequency of gravitational encounters. The black hole's immense but invisible presence began to tug at passing stars with greater regularity, bending their motions by fractions of a degree. These shifts were minute on human timescales, but enormous when projected across millions of years. The altered paths of these stars would subtly change the orbits of any planets bound to them, potentially triggering long cycles of climate instability or even planetary ejections. One of its early meetings in this busier sector came with a small open star cluster, perhaps only 100 million years old. These loose gatherings of young, blue stars burned hot and bright, their lifespans fleeting. The black hole's approach was not close enough to tear the cluster apart, but its gravitational influence stretched the delicate balance holding the stars together. The outermost members, already drifting from the cluster's gravitational grip, would be nudged farther, breaking away entirely to wander alone through the galaxy. If the black hole had passed directly through the cluster's heart, the result would have been catastrophic. Stars slingshotted into new orbits, some perhaps hurled out of the galaxy entirely, others pulled toward the black hole's waiting event horizon. But this encounter was glancing, a subtle reshaping rather than wholesale destruction. The black hole slid past, and the cluster continued its slow dispersal into the galactic disk, forever altered but not destroyed. Not long after, in the measure of galactic time, it entered the edge of a vast molecular cloud. Here, the density of gas and dust was high enough to obscure starlight entirely. These regions were cold, silent wombs where gravity slowly gathered matter into knots that would one day ignite as stars. The black hole's passage through such a place was invisible to outside observers, but within the cloud, it was a ghostly hand compressing some pockets of gas, disrupting others. A few of these disturbed clumps might collapse earlier than they otherwise would have, giving birth to stars, perhaps entire planetary systems, ahead of schedule. Others might be pulled apart, their eventual suns and worlds erased before they ever existed. In this way, the black hole acted as an unseen editor of the galaxy's future, deciding without intent which worlds would exist and which would never have the chance. Deeper in the spiral arm, the density of stars increased further, and the probability of close encounters rose. One such meeting involved a triple star system, two sun-like stars locked in a tight binary orbit with a smaller red dwarf circling far beyond. As the black hole approached, the binary pair was too tightly bound to be disturbed, but the red dwarf, already in a wide, slow orbit, felt the pull. Over thousands of years, its path stretched into an elongated loop until it finally broke free. The red dwarf became a rogue, set adrift in the interstellar dark, its feeble light illuminating only a tiny bubble of space. If it had planets, they would now be wanderers too, their nights eternal, their suns no more than a dim ember in the sky. Somewhere on one of those frozen worlds, if life had ever emerged, the black hole's passing would have been the cause of its ultimate exile. Moving ever closer to the crowded heart of the spiral arm, the black hole's journey intersected with a stellar stream, the remains of an ancient globular cluster torn apart by the Milky Way's gravity. The stars here were old, metal-poor, and densely packed compared to those of the galactic disk. Passing through the stream, the black hole deflected some stars inward toward the galaxy's core, while others were nudged outward into higher orbits. Each change, invisible in the moment, would play out across millions of years in the shifting architecture of the galaxy. For all these encounters, the black hole itself remained utterly unchanged. It absorbed nothing of consequence, emitted no light, and left no physical trace save for the altered motions of everything it touched. To follow its path was to read a story written only in gravity, a slow, looping script written across the spiral arms. The most dramatic event in this phase of its journey came when it passed through the outskirts of a supernova remnant. The explosion itself had occurred tens of thousands of years earlier, but its shock waves still rippled through the surrounding interstellar medium. The black hole sliced through the faintly glowing gas, its presence so small in physical size that the expanding shell barely noticed it. But deep within the cloud, where clumps of gas were still collapsing into new stars, the gravitational nudge could determine whether those newborn systems survived or were disrupted before they could stabilize. Astronomers, had they been watching from a safe distance, might have seen the faint X-ray flare that occurred when a loose wisp of supernova debris fell too close and was swallowed. For the briefest moment, the black hole's invisibility was broken, not by its own light, but by the destruction of something else. Then the glow faded, and it was gone again, a shadow moving deeper into the arm. This region of the galaxy was far from the Milky Way's central bulge, but every step inward brought denser star fields and higher velocities. The black hole's path, curved by the galactic potential, would eventually carry it closer to the central regions, though closer in this sense still meant thousands of light years. There, in the galaxy's core, the supermassive black hole Sagittarius A dominated, its own mass millions of times greater than our wanderers. Whether they would ever meet was uncertain. The stars, gas, and dark matter wove a complex web of gravitational influences, and over millions of years, small changes could lead to radically different outcomes. But if they did, the smaller black hole could be captured, spiraling inward over eons to merge with the giant. Such a collision would send a shudder of gravitational waves across the galaxy, marking the end of the wanderer's solitary existence. For now, though, it remained alone, its journey unending. Each encounter with clusters, clouds, stars, and planets was just another page in a story measured not in years, but in revolutions of the galaxy itself. The black hole had already circled the Milky Way many times since its birth, and it would circle it many more before its fate was decided. And somewhere, light years behind it, in a spiral arm already fading into the past, lay a small blue planet in a subtly altered orbit, one of countless worlds that had crossed paths with this dark traveler and been changed forever. The black hole's long, slow drift through the Milky Way's spiral arm eventually began to curve inward toward the galactic center. With every tens of thousands of years that passed, the density of stars increased. The sky here, if it could be seen through human eyes, would be a blaze of light. Stars were so close together that distances which, near the solar system, were measured in light years, could here be measured in mere light months. This was a realm of constant gravitational negotiation. Every massive object tugged on every other, each influence subtle but relentless. For a black hole, invisible and unlit, this was both an opportunity and a danger. A close pass with a massive star could alter its trajectory significantly, pulling it into a tighter orbit around the galactic center. A meeting with another compact object, a neutron star or another black hole, could set it on a collision course or fling it outward toward the galactic halo. One of its first encounters in this denser region came with a yellow giant star, bloated and nearing the end of its life. The black hole passed within a few dozen astronomical units, close enough for their gravitational fields to dance for a brief moment in cosmic terms. The giant's outer layers, tenuous and extended, shifted ever so slightly, rippling like a wind-blown veil. Had the black hole's approach been just a little closer, it could have begun stripping away that material, feeding for the first time in millions of years. Instead, it passed on, leaving the star to continue its slow march toward becoming a white dwarf. But the closer it moved toward the galactic center, the more chaotic its surroundings became. Star clusters orbited here in complex, overlapping paths, like a crowd of dancers moving to different rhythms. Some were bound tightly to the central supermassive black hole, Sagittarius A, their orbits taking mere thousands of years to complete. Others were new arrivals,
drawn inward from the spiral arms by the gravitational pull of the galactic core. It was among these clusters that the black hole had one of its most dramatic encounters since leaving the solar system. A globular cluster, ancient, dense, and spherical, lay in its path. The cluster's stars, numbering in the hundreds of thousands, were packed so closely together that the average distance between them was less than a light year. Moving through such an environment was like threading a needle through a swarm of bees. The black hole's gravitational influence was felt immediately on the outskirts of the cluster. The most weakly bound stars began to drift away, accelerated just enough to escape the cluster entirely. Deeper in, the passing shadow disrupted stable orbits, causing some stars to shift closer together, increasing the chance of collisions or mergers. For any planetary systems here, if any had survived the intense radiation and close stellar encounters typical of such places, the disruption would have been devastating. In the heart of the cluster, the density of stars was high enough that a close pass between two compact objects was not impossible. And indeed, the black hole's path brought it within a fraction of a light year of a neutron star. The encounter was brief but violent in gravitational terms, each object tugging at the other's velocity. The neutron star's path was altered, and the black hole itself took on a slightly new vector, one that would carry it even deeper toward the galactic core. As it moved inward, the pull of Sagittarius A began to dominate. Here, the stars orbited at breakneck speeds, completing loops in just a few centuries. These were the so-called S-stars, observed by astronomers in the early 21st century as they whipped around the black hole's invisible mass. For our wandering black hole, passing through this region was like entering a gravitational maelstrom. The supermassive black hole's gravity was so overwhelming that every object here was bound to its will. The question was not whether our traveler would be influenced, but whether it would be captured outright. A direct plunge toward Sagittarius A was unlikely unless it lost enough energy in a close encounter with another massive object, but the crowded nature of the region made such a loss possible. It was here that the black hole passed within a few light days of a massive O-type star, one of the few giants to survive so close to the galactic core. The encounter was close enough that the black hole's gravity distorted the star's shape, pulling it slightly toward a teardrop form. For a moment, material from the star's outer layers drifted outward, only to be pulled back by the star's own gravity. Had the black hole's velocity been just a little lower, it might have begun to siphon off this material, igniting a temporary accretion disk and producing a flare bright enough to be seen halfway across the galaxy. But the meeting was fleeting, and the black hole moved on. With every pass, it skirted the edges of gravitational traps, a slightly different angle, a slightly lower speed, and it might have been caught in a long, decaying orbit around Sagittarius A, spiraling inward over millions of years, until merging in a cataclysmic burst of gravitational waves. For now, it remained free, flung back outward into a looping trajectory that would carry it away from the very center, though not out of danger forever. In its wake, the galactic core continued its restless churn. Stars that had been nudged by the black hole's passing shifted their orbits subtly, setting up interactions that might not bear fruit for millions of years. Some would be drawn closer to the central supermassive black hole and devoured. Others might be ejected entirely from the galaxy, hurled into the intergalactic dark. As our traveler moved away from the densest part of the core region, it entered a zone where the stellar population thinned just enough for it to move unchallenged for tens of thousands of years. Here, the gravitational influences were gentler
the risks of capture lower. But the black hole's path still carried it along the inner galaxy, where the density of material was far greater than in the outskirts, where it had once passed near the Sun. This journey through the galactic center's inner regions would mark the most dangerous part of its orbit around the Milky Way. If it survived without being captured, it would begin a long outbound path, arcing back toward the quieter spiral arms. But such an arc could take millions of years, plenty of time for another chance meeting with a massive object to change its fate forever. For now, it remained what it had always been, a solitary wanderer, shaped by nothing but the pull of gravity, altering every world and star it passed without ever knowing or caring that they were there.
Leaving the crowded chaos of the galactic core behind, the black hole began a slow, outbound trajectory. Its path was not a straight escape. The gravity of Sagittarius A star still claimed it, curving its motion into a long, looping arc that would take millions of years to complete. But for the first time in ages, the density of stars around it began to thin. The crushing glow of the core's star fields faded into the more familiar darkness of interstellar space, punctuated by isolated points of light. Here, the black hole entered a transitional zone between the central bulge and the inner spiral arms. This was a region of stellar streams, great rivers of stars moving in the same direction, remnants of long-consumed dwarf galaxies or shredded globular clusters. From afar, these streams looked like faint filaments stretching thousands of light-years through the galactic disk. Up close, they were sparsely populated, the stars within them separated by light-years, but their motions were precise, their trajectory shaped by ancient gravitational tides. The black hole's passage through such a stream was like tossing a stone into a still pond. Stars at the edges of its influence bent slightly toward it, their velocities changed by small but permanent amounts. Over the coming millions of years, those tiny changes would ripple outward, subtly altering the shape of the stream. In some cases, the effect would be almost invisible. In others, the stream's graceful arc could warp into a faint S shape, a gravitational scar left by an intruder that had never even been seen. Farther along its path, the black hole crossed the orbit of an ancient, dying star moving alone through the void. This was a carbon-rich, asymptotic giant branch star, swollen, pulsating, and shedding its outer layers into space. A delicate shell of gas surrounded it, glowing faintly under the star's own fading light. The black hole passed within a fraction of a light-year away, its gravity tugging slightly at the star's tenuous envelope. In some distant future, that shell would expand unevenly, its perfect symmetry lost, a tiny, unremarkable change whose cause would never be guessed by any observer. As the years turned to tens of thousands, the black hole reached the outskirts of a spiral arm. Here, gas clouds grew more common again, drifting between clusters of young stars. These arms were not static structures, they were waves of density, places where the material of the galaxy was compressed enough to ignite star formation. The black hole's path carried it along the edge of one such wave, where new suns were being born from cold molecular clouds. Though it would never be close enough to tear these clouds apart, its gravity still exerted a subtle pull. In one particularly dense clump, the extra compression caused by its passing might be enough to hasten the collapse of a protostar by a few thousand years, a blink on the cosmic scale, but a shift in the timeline that could alter the evolution of whatever planetary system would form there. A planet that might have existed could be denied by this change. Another, perhaps with its own future life, could be created sooner than it otherwise would have been. The spiral arm itself was a tapestry of life cycles. Here were massive blue stars burning through their fuel in just a few million years, destined to end in supernova explosions. Here too were fragile red dwarfs, barely sipping their fuel, and destined to outlive the galaxy's brightest giants by trillions of years. The black hole drifted among them unnoticed, a shadow that only the most sensitive instruments could ever hope to detect. Its next encounter of note came with a loose association of young stars, a moving group born from the same cloud but already beginning to disperse. Among them was a star with a wide, cold gas giant orbiting at hundreds of astronomical units. The black hole's approach altered the gas giant's path by the smallest of margins, stretching its orbit into a more elongated ellipse. The change was so small that it might take millions of years for the planet's host star to feel its full effect. But over enough time, such perturbations could destabilize distant companions, either sending them inward toward the star or ejecting them into interstellar exile. Beyond this young association lay a darker, emptier stretch of space. The black hole now moved into the quieter parts of the spiral arm, where star formation had slowed. Here, the stars were older, many of them nearing the ends of their lifespans. White dwarfs, the burnt-out cores of sun-like stars, drifted alongside orange and red dwarfs that could still shine for trillions of years. These were cosmic survivors, moving steadily along paths that had been stable for billions of years. But even here, the black hole's presence was a quiet disruptor. One white dwarf in particular would feel its influence more strongly than most. Orbiting the dead star was a debris disk of asteroidal fragments, the remains of planets destroyed when the star had expanded into a red giant long ago. As the black hole passed, its gravity shifted the trajectories of some of these fragments. Over time, more and more of them would spiral inward, falling onto the white dwarf's surface. The infalling matter would ignite brief, faint bursts of light, nova-like events that would flicker and fade in days, unnoticed by except the most attentive observers. The outbound journey from the galactic core was long and meandering. The black hole was not on a mission, not following any conscious path. It was simply obeying the geometry of space-time. Every pass near a star or cluster bent its path slightly, ensuring that no two orbits of the galaxy would ever be exactly the same. In millions of years, it might return to the central regions. In billions, it could wander to the galactic halo, far above or below the disk. But for now, its route kept it within the inner disk, weaving between arms, touching gas clouds, star clusters, and lonely wanderers. Each encounter left behind a faint gravitational fingerprint. A planet shifted, a star's motion altered, a future system's destiny rewritten. These changes were too small to notice in a single lifetime, but together they were part of the ongoing reshaping of the galaxy itself. As the spiral arm curved away beneath it, the black hole approached another stellar stream, this one the remnant of a satellite galaxy consumed by the Milky Way hundreds of millions of years earlier. The stars here moved like a slow, shimmering ribbon across the darkness. Passing through it, the black hole tugged gently at their motions, changing the stream's width and speed in ways that long from now would alter its eventual dispersion into the galactic background. It was a reminder that even without swallowing stars or planets, a black hole could still be one of the most influential travelers in the galaxy. Its work was silent, invisible, but permanent. And as it moved onward, deeper into the spiral structure, there was no sign that its journey would ever end, unless it met something massive enough to stop it. Ahead lay another dense knot of stars, and beyond that, the open gulf between spiral arms, a vast, dark sea that would take tens of millions of years to cross. The black hole drifted toward it, unaware and unconcerned, its influence stretching invisibly behind it like a wake across the Milky Way.
The black hole crossed the outer edge of the spiral arm and entered the vast gulf of interarm space, a region where the density of stars fell sharply and the distances between them stretched into dozens of light-years. Here, the Milky Way's structure loosened, the glowing lanes of gas and dust left behind, replaced by a colder, lonelier void. This was a desert in galactic terms. No star-forming regions glowed here, no crowded clusters shimmered in the dark. The few stars that did exist in this realm were wanderers, some flung out from spiral arms by gravitational interactions, others drifting in quiet orbits that happened to take them between the galactic highways of matter. The black hole's path through this region would be long and uneventful by the measure of stellar encounters, but not without its own subtler forms of influence. One such encounter came with a solitary red dwarf star, a faint ember barely larger than Jupiter, but with a mass dozens of times greater. It had no close neighbors, no planets, only a few asteroidal bodies locked in distant, cold orbits. The black hole passed within half a light-year, far enough that no material was drawn toward it, yet close enough to alter the dwarf's galactic trajectory by a fraction of a kilometer per second. That change was trivial in human terms, but over tens of millions of years, it would bend the star's orbit, eventually carrying it toward a spiral arm it would otherwise never have entered. Farther into the void, the black hole approached a rogue planet, a frozen gas giant ejected from its home system billions of years earlier. Drifting through interstellar space, the planet was wrapped in a deep shroud of methane ice, with an atmosphere long since collapsed to the surface. The black hole passed close enough to bend its path, subtly redirecting its endless journey. That shift could, far in the future, bring the planet into the gravitational influence of another star, giving it a second chance to orbit a sun after an eternity of darkness. But in between these rare meetings, the black hole moved through emptiness. For thousands of years at a time, there was nothing within even a light-year, no stars, no planets, only the thin haze of the interstellar medium, a few atoms of hydrogen and helium drifting in each cubic centimeter. Occasionally, it would encounter a slightly denser region, a wisp of gas left behind by an ancient supernova, and for a brief moment, matter would spiral inward, heating just enough to release the faintest whisper of X-rays. These events were so weak that no civilization, even with the most advanced instruments, would detect them unless they were almost upon the black hole itself. This was the purest expression of its nature: invisibility, silence, and yet a gravitational presence that extended for light years. Even here, in the emptiest spaces, the curvature it created in space-time reached outward, pulling subtly on everything nearby. For millions of years, the black hole would traverse this desert. Its motion, still dictated by the great curve of its galactic orbit, was slow and constant, bringing it ever closer to the next spiral arm ahead. From this vantage, the Milky Way's arms appeared not as rigid structures, but as moving waves of matter, slowly rotating around the galactic center. The arm it was approaching was younger and more active than the one it had left, its lanes of dust already visible as a faint smudge even from dozens of light-years away. But the crossing from one arm to another was measured in deep time. Entire civilizations could rise and fall before the black hole reached the bright edge of the next wave of stars. In that time, its influence on inter-arm space would be minimal but not non-existent. It could still catch a rogue comet drifting between systems, pulling it into a new trajectory that might, in eons, bring it into the orbit of a distant star. It could still alter the galactic path of a lone brown dwarf, changing the timing of an encounter it might have with another object millions of years hence. There was an eerie beauty to its solitude here. In the denser regions of the galaxy, the black hole had been one influence among many, its gravity mingling with that of countless stars, clusters, and nebulae. Here, in the sparse reaches between arms, it was almost alone in its dominion. Each encounter it had was cleaner, less muddled by competing forces, and the changes it wrought were simpler to trace through the tapestry of future events. Eventually, it would come upon a drifting stellar remnant, a neutron star traveling alone, its radio pulses long dead, its surface cooled to near invisibility. The two objects, both born from the deaths of massive stars, passed within a light year of each other. The gravitational dance was subtle but profound. The neutron star's path bent slightly inward toward the black hole before its momentum carried it past, like two ships brushing wakes in a dark ocean. Neither object was aware, neither altered in appearance, but both carried away a new trajectory that would echo for tens of millions of years. Onward the black hole drifted, deeper into the void, the spiral arm ahead still decades of thousands of years away at its current speed. The interstellar medium here was so thin that in a cubic kilometer of space, there might be less mass than in a single grain of sand. And yet, on a cosmic scale, the black hole was moving through a river, the galactic disk's rotation carrying stars, dust, and dark matter along in vast, slow currents. It was in these currents that the black hole's true nature as a sculptor of fate was most apparent. Even without accreting matter or colliding with stars, its path through the galaxy was one long chain of gravitational edits. Here a star shifted, there a rogue planet redirected, elsewhere a distant comet's course altered in such a way that it would one day blaze in some other sky. As it neared the halfway point of its journey through the void, the black hole passed a tenuous veil of interstellar dust, the remains of an ancient molecular cloud that had been shredded by stellar winds. The particles were too sparse to form anything new, but in the presence of the black hole's gravity, some strands of dust twisted and coiled into faint arcs, altering the delicate, invisible structure of the medium itself. Finally, after an epoch of emptiness, the density of matter ahead began to rise again. Faint background stars grew brighter and more numerous. Wisps of nebular gas glowed faintly, illuminated by the ultraviolet light of hot young stars just beyond the horizon. The black hole was approaching the edge of the next spiral arm, and with it a new era of encounters, influences, and possible danger. Behind it, the interarm gulf settled back into stillness, its few altered stars and wandering planets carrying the memory of the encounter forward into the deep future. Ahead lay the crowded star fields and restless dynamics of a galactic highway, a place where the black hole's silent passing could again change the destinies of countless worlds. The first signs of the spiral arm ahead were faint but unmistakable. Against the backdrop of interarm darkness, a diffuse band of light began to swell, not from a single source, but from the combined glow of millions of stars. The black hole moved toward this region like a shadow drifting into firelight. Here, the density of matter would rise sharply, and with it the frequency of encounters. Crossing the outer edge of the arm, it first passed through a field of hot, massive O and B-type stars. These stellar giants lived fast and died young, their lifetimes measured in mere millions of years. Their ultraviolet radiation carved cavities in the surrounding interstellar medium, sculpting the gas into glowing arcs and pillars. The black hole slid invisibly through this chaos, its path slightly warping the motions of smaller stars that happened to lie near its trajectory. Within a few thousand years of entering the arm, it encountered its first significant feeding opportunity in ages. A small low-mass star orbited a swollen red giant companion in a loose binary system. The pair was already unstable, their orbits shifting under the tidal influence of the giant's extended atmosphere. The black hole's approach tipped the balance just enough to pull the smaller star outward, breaking the binary apart. Freed from the smaller star's gravitational anchor, the red giant began shedding material more rapidly into space.
and some of that gas drifted into the black hole's reach. For a brief time, an accretion disk formed, thin and pale, but hot enough to emit faint X-rays. The flare was weak compared to the furious feeding of black holes in dense galactic centers, but in the quiet outskirts of a spiral arm, it was a beacon. Any advanced civilization within a few hundred light-years could have detected it, a sudden, short-lived whisper of destruction against the cosmic background. But as quickly as it came, the flare faded. The black hole moved on, leaving the red giant to continue its lonely decay. Farther into the arm, it passed near a dense molecular cloud, a dark, cold mass stretching dozens of light-years across, invisible light, but glowing faintly in radio wavelengths. These clouds were the cradles of new stars, their gravity slowly pulling them into knots of increasing density. The black hole's approach disturbed the edges of the cloud, compressing some regions while unraveling others. In one corner, the extra squeeze would cause a protostar to collapse early, setting into motion the birth of a new planetary system millions of years ahead of schedule. In another region, turbulence would scatter a forming clump, preventing a star from ever igniting. The deeper it went, the more frequent the interactions became. The spiral arm's crowded environment meant that every few 100,000 years, it passed close enough to some massive object to leave a permanent mark. One such encounter came with a young star cluster, still partly embedded in its birth cloud. Dozens of bright blue stars blazed in its core, surrounded by smaller, cooler companions. The black hole's pull was just enough to alter the orbits of a few peripheral stars, sending them drifting outward. For planets in those stars' habitable zones, if any existed, the change would be gradual but profound, slowly modifying the amount of stellar light they received over thousands of years. At one point, the black hole crossed a path just a few light days from a solitary white dwarf with a close-orbiting gas giant. The giant's atmosphere, already stretched thin by tidal forces, spilled material toward its parent star in a shimmering stream. The black hole's passing disturbed the delicate balance, intensifying the flow. In the years that followed, the giant would shrink, its atmosphere stripped away more rapidly than before until only a scorched, rocky core remained, a planet reduced to a husk by the combined forces of its star and the invisible traveler. In the spiral arm's inner lanes, the black hole drifted into the vicinity of a supernova remnant only a few thousand years old. The expanding shell of gas and dust glowed in X-rays and radio waves, a hot bubble of chaos. Passing through its outskirts, the black hole's gravity bent the paths of shockwave fragments, altering their trajectories just enough to change how they interacted with surrounding gas clouds. Such tiny changes could influence whether certain regions collapsed into new stars or dispersed into the interstellar medium. The most dramatic moment of this stretch of the journey came when the black hole passed through a loose binary system consisting of a neutron star and a main sequence companion. The system was already unstable, with the neutron star drawing gas from its partner in occasional bursts. The black hole's gravitational pull destabilized the orbit further, tightening the pair's dance and accelerating their eventual merger. In tens of millions of years, the two would collide, producing a kilonova, a brilliant, short-lived explosion that would forge heavy elements like gold and platinum before fading into darkness. The black hole's passing would be long forgotten by then, but its influence would be written into the timing of that distant, spectacular event. Moving ever deeper into the spiral arm, the black hole encountered a region rich in open clusters and stellar associations. The gravitational interplay here was complex, with groups of stars drifting apart as they aged and interactions with passing objects, like our black hole, hastening their dissolution. Some stars, gently tugged by its pull, would end up wandering into interstellar space.
Others would drift toward denser parts of the arm, perhaps finding new companions. All the while, it remained invisible except for those rare moments when matter crossed the event horizon. Unlike stars which announce themselves with light, the black hole story could only be read in the altered paths of others. A planet's climate changing over millennia, a comet arriving early in a system's history, a star leaving its cluster centuries ahead of schedule. These were the quiet sentences it wrote in the Book of the Galaxy. Eventually, the density of the spiral arm began to ease. The black hole was approaching its far edge, where the brilliant star fields thinned and the interstellar medium became more transparent. Ahead lay another inter-arm gulf, a stretch of relative quiet before the next wave of matter and light. But in its wake, the arm was subtly changed. Some systems had been pushed toward instability, others nudged into long-term stability they might never have achieved without the passing shadow. Star-forming clouds had been seeded with early births or stripped of their potential entirely. In the long future, civilizations might arise on worlds that owed their very existence or their absence to this single, silent traveler. The black hole drifted onward, leaving the bright lane of the spiral arm for the darkness beyond. It had no awareness of what it had done, no record of the changes it had made, and yet across thousands of light years, its influence would echo for millions of years to come. As the black hole left the glowing bustle of the spiral arm behind, the galaxy began to thin once more. The stars grew sparser, the bright blue giants and sprawling nebulae of the arm fading into the background. Ahead lay the faint and scattered domain of the galactic outskirts, the edge of the disk where the ordered lanes of the Milky Way gave way to the diffuse, mysterious halo. Here, the black hole's path gradually tilted upward, lifting it above the flat plane of the galactic disk. The motion was not intentional, nothing it did ever was, but the result of countless past encounters that had nudged its velocity in subtle directions. Now, over the course of hundreds of thousands of years, that vertical motion would carry it far above the luminous heart of the Milky Way, into the realm where the galaxy's grand structure could be seen in its entirety. The transition was gradual. At first, the spiral arm still loomed below, arcs of starlight threading through lanes of dust. But as the black hole climbed higher, their patterns became clearer, rivers of stars curling around the galactic core, some bright and well-defined, others pale and dissolving into the surrounding dark. The Milky Way's central bulge glowed with a faint golden hue, its billions of stars compressed into a brilliant, glowing sphere. In this lofty region, encounters with other objects were rare. The halo was populated mainly by ancient low-mass stars and the remnants of long-dispersed clusters. Many of these stars had orbits that carried them far above and below the galactic plane, tracing elongated ellipses around the core. The black hole's passage here would not be marked by frequent disruptions, but by the occasional, long-reaching pull on one of these solitary wanderers. One such encounter came with an ancient subdwarf star, a relic from the earliest days of the Milky Way, older than most of the elements in the human body. Its orbit around the galaxy was nearly polar, carrying it far out of the disk before plunging back through the crowded plane. The black hole passed within a light year, altering its path by the slightest of margins. This slight deflection would not be noticeable for millions of years until the star's altered trajectory brought it into an unusually close pass with the galactic center, a meeting that might, in the far future, strip away any remaining companions or debris. Higher still, the black hole anchored the realm of globular clusters, dense spherical swarms of hundreds of thousands of stars bound together by gravity. These clusters orbited the galaxy like ancient satellites, most of them older than the Milky Way's spiral arms themselves. Passing near one such cluster, the black hole tugged faintly at its outermost members, pulling a few into new, more elongated orbits around the cluster's core. In the slow ballet of stellar dynamics, these tiny changes could eventually contribute to the cluster's gradual dissolution into the halo. From this vantage point, the galaxy's halo revealed its other, invisible component, dark matter, Though unseen, it accounted for most of the mass here, forming a vast spherical envelope that extended far beyond the visible stars. The black hole moved through this invisible sea as if through air, feeling its presence only through the way it shaped the orbits of everything else. In this rarefied environment, the black hole's gravitational influence could extend farther without competition from nearby stars. A faint, distant binary system, two dim red dwarfs orbiting one another, felt its approach despite being several light-years away. Their orbit shifted minutely, the period between their revolutions changing by a fraction of a second. No light flared, no matter was swallowed, but the change was permanent, written into the system's future. Occasionally, the black hole would pass through the trail of a disrupted dwarf galaxy, a stellar stream stretching for thousands of light-years, the shredded remains of a small galactic companion that the Milky Way had consumed eons ago. In such a place, the density of stars was still higher than the surrounding halo, and the black hole's influence could scatter them into new paths, widening the stream's already ragged edges. The climb into the halo eventually reached its peak. From here, the Milky Way's disk lay far below, a glowing spiral suspended in the dark. Its arms were pale and ghostly at this distance, their colors muted, but the sheer scale of the structure was breathtaking. Hundreds of billions of stars swirling in slow, majestic rotation. The galactic core gleamed at the center, wrapped in veils of dust and haloed by faint light. From this height, the black hole's orbit would eventually begin to bend downward again, drawing it back toward the disk. But the arc of its motion was vast. It would take millions of years to descend, passing again through the disk and perhaps deep into another spiral arm. In the meantime, it would drift along the outer rim of the galaxy, where the halo began to fade into intergalactic space. Here, at the extreme edge of the Milky Way's gravitational domain, it was possible for encounters with truly alien objects, visitors from beyond the galaxy, to occur. Rogue stars ejected from neighboring galaxies, intergalactic gas clouds, even other black holes could pass through this region. Most would come and go without incident, but in the rare case of a close approach, the trajectories of both objects could be dramatically altered, sending one deeper into the Milky Way and flinging the other outward into the cosmic void. For the black hole, the halo offered freedom from the constant gravitational noise of the disk. It moved here like a silent predator in a vast, dark savanna, its influence reaching farther, its presence felt more clearly by the few objects that wandered near. Yet even here, its life was defined not by hunting or feeding, but by the endless drift, a motion inherited from its birth, unbroken by any force in the universe save the pull of gravity itself. Eventually, the long looping arc of its orbit would carry it back toward the disk. Ahead lay the faint glow of another spiral arm, a promise of denser star fields and richer encounters. The black hole, indifferent as ever, continued forward, unaware of the stories it had already written into the motions of stars, planets, and clouds behind it, and of those it was yet to write in the ages to come. The long descent from the halo back into the galactic disk was as slow and patient as the climb had been. Over millions of years, the black hole's arc curved downward, carrying it toward the flat, glittering plane of the Milky Way. From its lofty vantage point, the spiral arms had appeared as delicate threads. Now, as it drew nearer, their light swelled and scattered into countless individual suns. The arm it was approaching was older, quieter than the ones it had passed before. Many of its most massive stars had long since burned out, leaving behind swarms of long-lived dwarfs and the white embers of stellar corpses. Gas and dust were present but sparse. Star formation still occurred, but in isolated pockets rather than vast, luminous nurseries. As the black hole crossed the boundary into this arm, it encountered the gravitational pull of a mid-sized open cluster. The cluster's stars were bound in a loose, slow dance, many already drifting away into the surrounding space. The black hole's approach quickened that dissolution. A handful of peripheral stars were nudged outward, their motions subtly reshaped so they would never return to the group. In a few 100 million years,
the cluster would disperse entirely, its members scattered across the galaxy, a process sped along by an intruder they never saw. Not long after, it came upon a sun-like star with a small retinue of planets. The system lay at the quiet edge of the spiral arm, far from any disruptive stellar neighbors. For billions of years, its orbits had been nearly perfect, the planets circling in serene regularity. The black hole's passage, though distant, was enough to shift the outermost planet's path. The change was tiny, a fraction of a percent in its orbital period, but over time it could have profound effects. If the planet harbored moons, their tidal patterns would alter. If it hosted life, climates might slowly drift toward new regimes, reshaping ecosystems over geological ages. Deeper into the arm, the black hole crossed the remains of a stellar association, a moving group of young stars that had long since shed the cloud of their birth. Many were solitary now, scattered like sparks from a dying fire. The black hole passed quietly among them, tugging at one or two just enough to change the future pattern of their motions through the galaxy. Far ahead, the density of stars thinned again, but not into the emptiness of inter-arm space. Instead, the black hole was moving toward a region of the disk with striking similarity to the one it had crossed hundreds of millions of years earlier, the part of the Milky Way where a small yellow star orbited quietly with its own set of planets, a place like the solar system. It was not the same neighborhood. The galaxy's slow rotation and the black hole's wandering path ensured that it would never return to the exact scene of its earlier influence. But the resemblance was uncanny. A modest, stable star surrounded by planets of rock and gas, dust belts, and wandering comets in a distant cloud. Somewhere among these worlds, perhaps, life might exist, looking up at the night sky, unaware that an invisible shadow was passing through the depths of their local space. The black hole's trajectory carried it far beyond the planetary zone, missing the inner worlds by light years. But even at that distance, its gravity reached out, stirring the most distant objects, icy bodies in a scattered halo, dark asteroids in wide orbits. Some would be nudged toward the star, beginning long elliptical paths inward. In ages to come, they might blaze as comets in alien skies, inspiring myths and superstitions among whatever minds might be there to witness them. Others would be thrown outward, cast loose into the galactic wilderness, to wander between stars for eternity. From the perspective of any local civilization, this would be an invisible event. No light, no sound, no direct sign of danger, only a subtle rewriting of the architecture of their home system. But the changes would be lasting, carried forward in altered orbits, shifted climates, and rare but significant impacts. After this quiet disruption, the black hole continued on. It crossed the arm in stately silence, weaving between solitary dwarfs and faint binaries, never touching them directly, yet always altering the invisible web of gravity that bound them together. Beyond the far edge of the arm, the starlight began to thin once more, giving way to another expanse of relative darkness. It had now completed yet another loop of its endless path around the Milky Way, one of countless revolutions it had made since its birth in the heart of a long-dead star. The galaxy itself had changed over those eons. Arms shifted, clusters formed and dissolved, stars were born and died. Yet the black hole endured, timeless and indifferent, a piece of collapsed matter with no purpose beyond the inevitability of its own motion. In the deep future, its orbit might change drastically. A close pass with another massive object could send it hurtling toward the galactic center, to merge at last with Sagittarius A1, sending ripples of gravitational waves through the fabric of space. Or it could be flung outward into the galactic halo, or even beyond, escaping the Milky Way entirely to drift between the galaxies. Each possibility depended on chance encounters that could happen tomorrow or 10 billion years from now. But until that day came, it would remain as it always had been, silent, unseen, and inescapable. It would pass through bright regions and dark voids, among the young and the ancient, touching each with a gravity that left no mark visible to the eye, but could reshape the destiny of worlds. The Milky Way's vast arms would turn, slowly carrying stars and planets along their winding paths. Civilizations might rise, study the sky, detect its shadow in the way stars drift from their expected courses, and name it with words of fear or reverence. Or they might never know it had been there at all. For the black hole, their awareness or ignorance made no difference. It did not seek, it did not flee, it did not think. It only moved. And so it traveled, a perfect engine of gravity, a fragment of collapsed time and space, the most dangerous object in the universe, not because of what it chose to do, but because it could never be stopped.